Jantar Mantar, and for that I will hand over the mic to Professor Indumati.
Thanks. Thank you. So it's really a pleasure to have this very short ceremony. You may know that IMSc has been a part of Tamil Nadu Science Forum for decades now, starting from Professor Ramchandran, who is sitting here as director of IMSc. IMSc has always supported activities of Tamil Nadu Science Forum through its writings and through other popular activities, including going out to schools and colleges and giving talks. As part of that celebration of IMSc 60, we are having a small program. We are releasing actually a collection of articles which were written by people from IMSc, students, postdocs, faculty, over the last 15 years. Actually, about 8 years ago, we celebrated 25 years of Jantar Mantar. So that was a collection that was released at that time. That's why I only took the last 15 years worth of collection, and we have selected out some articles written by IMSc members and brought out this collection over here. And okay, those who want can read that small script. But so we now have some of our Science Forum friends who have come to celebrate the occasion along with us. So let me call to the stage S. Subramani, who is General Secretary of Tamil Nadu Science Forum. No. IMSc people will come late, I know. S.T. Balakrishnan, Secretary TNSF. He's the coordinator for Tulir, which is a sister magazine, which is a monthly magazine coming out in Tamil, also a children's science magazine. Muhammad Badusha, Secretary Publications, who was responsible for bringing it out on time so we could release it today. Jeevanandam, Treasurer of Tamil Nadu Science Forum. Sudhakar, who is Secretary of the Chennai District of Tamil Nadu Science Forum, Chennai chapter, of which, by the way, I am honorary president. Very honorary, I don't do anything. C. Ramlingam, also from the Chennai chapter. So we really thank our colleagues who work very hard to bring this collection out on time. Now it's my pleasure to invite the director of IMSc, Professor V. Ravindran, who has long been a member of Tamil Nadu Science Forum and has participated in its activities ever since he was a PhD student over here. I also invite Professor M.V.N. Murthy, who will hand over the first copy to Professor Ravindran. Go. If you come late, you won't get your instructions. Go. You want to come? No, Vanda. Avaru Tulirukku varuvaanga.
He's a real tough one. Huh?
Go.
Students are usually tough for their guides.
Yeah, it's also my pleasure to tell you that both Ravindran and I have been students, PhD students of Murthy, okay? So he was very upset when we were doing all this work instead of doing Science Forum activity. So I now request Mr. Badusha to make a report. They have been working very hard over the last 1 year through the support of IMSc and have participated in IMSc 60 celebrations across the districts of Tamil Nadu. So he will now tell us all about it. There will be a short translation of this by Ramanujam afterwards.
ஹலோ, அனைவருக்கும் வணக்கம். ஒரு மிகச்சிறந்த நிகழ்வு இது. தமிழ்நாடு அறிவியல் இயக்கத்திற்கும் ஐஎம்எஸ்சிக்குமான தொடர்பு மிக நீண்ட தொடர்பு. தமிழ்நாடு அறிவியல் இயக்கம் தன்னுடைய முத்திரை நிகழ்ச்சியாக லிட்ரஸி மிஷன் ப்ரோக்ராமை சொல்லுவாங்க. அறிவியல் இயக்கம் தமிழகத்தில் நடக்கும்போது இருந்து இந்த ஐஎம்எஸ்சியிலிருந்து பல பேர் அந்த நிகழ்ச்சியில் பங்கெடுத்திருக்காங்க. தொடர்ந்து தமிழ்நாடு அறிவியல் இயக்கத்தின் மிக முக்கியமான படைப்பான துளிர், ஜந்தர் மந்தர் என்ற இரு இதழ்கள் தமிழகத்தில் மிக மதிப்பிற்குரிய இதழ்களாக இருக்குது. தமிழில் துளிரும், ஆங்கிலத்தில் ஜந்தர் மந்தரும். இந்த இரண்டு இதழ்களின் ஆசிரியர்களும் இந்த இன்ஸ்டியூட்டில் இருந்து தான் வந்திருக்காங்க. இதுவரைக்கும் கடந்த 35 ஆண்டுகளாக மிக முக்கியமான இதழ்களை தமிழக மாணவர்களுக்கு தந்து கொண்டு இருக்கிற நிறுவனம் இது. எங்களை தமிழ்நாடு அறிவியல் இயக்கத்தின் சார்பில் இந்த நிறுவனத்திற்கு நன்றியும் பாராட்டுகளையும் தெரிவித்துக் கொள்கிறோம். இந்த நிறுவனத்தின் 60ஆம் ஆண்டு விழாவை செலிப்ரேட் பண்ணணும்னு சொல்லும்போது அது எங்களுக்கு ஒரு மிக முக்கியமான நிகழ்ச்சியாக இருந்துச்சு. குறிப்பாக ஐஎம்எஸ்சின் 60ங்கிறது ஐஎம்எஸ்சிக்கல்ல தமிழ்நாட்டுக்கு மிக முக்கியமான ஒரு நிகழ்வு. அறிவியல் இயக்கத்திற்கும் நிறைய படைப்புகளை தந்த இடம் அது. அதனால் அது நாங்களும் மிக முக்கியமாக செலிப்ரேட் பண்ண நினச்சோம். அதுக்காக ஒரு திட்டத்தை முன்மொழிந்து ஐஎம்எஸ்சியோட சப்போர்ட்டை கேட்டிருந்தோம். அவங்களும் சப்போர்ட் பண்ணாங்க. அந்த வகையில் கடந்த ஒரு வருடமாக நடந்த நிகழ்வுகளை ஒரு சிலதை உங்கள் முன்னில் வைக்கணும்னு நினைக்கிற இந்த இடத்துல. குறிப்பாக கடந்த 2022 ஜனவரி 3 அன்னைக்கு இதே நிகழ்ச்சியில் இந்த துளிர் மற்றும் ஜந்தர் மந்தருடைய தொகுப்பு புத்தகத்தின் முகப்பை வெளியிட்டோம். ஒரு கண்காட்சி வெளியே அமைச்சிருந்தோம். ஜந்தர் மந்தர் புத்தகங்களின் அட்டை ரேப்பர் எக்ஸ்போ ஒன்று வச்சுருந்தோம் முன்னால் 2022 ஜனவரி 3 அன்னைக்கு. அதே சமயம் மேக்ஸை பற்றி ஒரு அவேர்னஸ் கொடுக்கணும். ஒன்று மேக்ஸ் சம்மந்தமான இன்னொரு இன்ட்ரெஸ்ட் ஏற்படுத்துறதுக்காக ஒரு ஆன்லைன் செமினார் ஒன்று நடத்துறதுக்கான முயற்சிகளை பண்ணோம். அதில் ஆச்சரியமாக ஒரு மேக்ஸ் கணக்கில் நான் வீக்குன்னு எல்லாம் பேசுவாங்க. ஆனால் ஆச்சரியம் அந்த நிகழ்ச்சிக்கு ரெஜிஸ்ட்ரேஷன் வந்து 6500 பேர். ஒரு ஆன்லைன் ப்ரோக்ராமுக்கான ரெஜிஸ்ட்ரேஷன் நாங்களே எதிர்பார்க்காத ஒன்று. 6500 ரெஜிஸ்ட்ரேஷன் பண்ணாங்க, கலந்துக்கிட்டாங்க. மிக சிறந்த நிகழ்ச்சி அது அமைச்சது. ஒரு முத்திரை நிகழ்ச்சி அது இருந்துச்சு. அடுத்து தேசிய அறிவியல் தினத்தை முன்னிட்டு 2022 தேசிய அறிவியல் தினத்துக்காக நேஷனல் சயின்ஸ் டேக்காக ஒரு ஸ்டேட் ஃபுல்லாக ஒரு 1000 இடங்களில் சயின்ஸ் எக்ஸ்போ நடத்தணும் அல்லது சயின்ஸ் லெக்சர் நடத்தணும் முயற்சி பண்ணோம். அதே நிகழ்ச்சி சயின்ஸ் ஃபாரம் ஐஎம்எஸ்சி சேர்ந்து அந்த நிகழ்ச்சியை ஆர்கனைஸ் பண்ணோம். கிட்டத்தட்ட 1000க்கு மேல் இடங்களில் ஏறக்குறைய 1500 இடங்களில் அந்த நிகழ்ச்சி நடந்துச்சு. தமிழ்நாடு முழுக்க 1500 இடங்களில் இந்த தேசிய அறிவியல் தின நிகழ்ச்சி 3 நாட்கள் நடந்துச்சு. குறிப்பாக அந்த நிகழ்ச்சிக்காக சர் சி வி ராமனுடைய ஒரு மாஸ்க் ஒன்று கொடுத்துருந்தோம், ஒரு புத்தகம் ஒன்று கொடுத்துருந்தோம். 14,800 பேருக்கு மாநிலம் முழுக்க கொடுத்தோம். மிகப்பெரிய நிகழ்ச்சியாக நடந்துச்சு. ஒரு முக்கியமான நிகழ்ச்சி 1500 இடங்கள் பக்கம் நடந்துச்சு. அந்த சமயத்தில் ஒரு 3 நாட்கள் நிகழ்ச்சி தொடர்ந்து நடந்துச்சு. தமிழகம் முழுக்க பல்வேறு இடங்களில், நிறுவனங்களில், பள்ளிகளில், பொது இடங்களில் இந்த நிகழ்ச்சி நடந்துச்சு. அடுத்து ஐஎம்எஸ்சியோட 60க்காக ஒரு சில மேக்ஸ் செமினார்ஸ் நடத்தலான்னு திட்டமிட்டோம். மேக்ஸ் செமினார்ஸ், மேக்ஸ் ஒர்க் ஷாப்லாம் அது இதுவரைக்கும் 12 மாவட்டங்களில் நடந்திருக்குது. கிட்டத்தட்ட 1000க்கு மேலே பங்கெடுத்திருக்காங்க. அந்த மாவட்டங்கள் கூட தமிழ்நாட்டில் பெரம்பலூர், கடலூர், திருச்சி, மதுரை, கோவை, சேலம், விருதுநகர், கன்னியாகுமரி, திருப்பூர், ராமநாதபுரம், திண்டுக்கல், கிருஷ்ணகிரி உள்ளிட்ட 12 மாவட்டங்களில் ஒர்க் ஷாப் நடந்திருக்குது. 1000க்கு மேலே இல்லம் தேடி கல்வி வாலண்டியர்ஸு, ஸ்டெம்முடைய கருத்தாளர்கள், டீச்சர்ஸு, துளிரில்ல பொறுப்பாளர்கள் கலந்துருக்காங்க. ஒரு முக்கியமான நிகழ்ச்சி அது இருந்துச்சு. அது இன்னும் தொடருது. அடுத்து உலக புத்தக தினம் ஏப்ரல் 23 நடந்துச்சு. அதுக்காக ஒரு சில புத்தகங்களை தயாரிக்க முடிவு பண்ணியிருந்தோம். அதில் குறிப்பாக ஐஎம்எஸ்சி 60க்காக சிறப்பு வெளியீடாக 8 கணித நூல்களை வெளியிட்டோம். தமிழகத்தில் முதல் முறையாக மாணவர்களுக்காக சிறப்பாக தயாரிக்கப்பட்ட படக்கதைகளோட ஒரு புத்தகம், கணிதம் சார்ந்து 8 புத்தகங்களை வெளியிட்டோம். அது இந்த இடத்துல இந்த நிகழ்ச்சி நடத்தி பள்ளிக்கல்வித்துறை இயக்குனர் கலந்துட்டு புத்தகங்களை வெளியிட்டாங்க. அது ஒன்றும். அதே போல் ஐஎம்எஸ்சி 60க்காக பேராசிரியர்கள் ஃபோரம் ஒன்று உருவாக்கலாங்க ஐடியாவில் ஒரு பேராசிரியருக்கான ஒரு செஷன் இங்கே நடந்துச்சு. அவங்க தங்களுடைய இன்றைக்கி இருக்க எஜுகேஷன் சூழல், அவங்க கல்வி நிறுவனத்தில் உள்ள சூழல் பற்றியெல்லாம் பேசுகிறாங்க. ஒரு முக்கியமான அமர்வாக இருந்துச்சு. 100 பேராசிரியர்கள் மாநிலம் முழுக்க தன்னார்வமாக கலந்துக்கிட்டாங்க. இதெல்லாம் இதுவரைக்கும் நடந்திருக்குது. தொடர்ந்து சின்ன நிகழ்வு நிறைய நடந்துட்டுருக்குது. இப்போது ஜந்தர் மந்தருடைய ஒரு முக்கியமான தொகுப்பு இங்கே வெளியிட போகிறோம். இது ரொம்ப முக்கியமான ஒரு தொகுப்பாக இருக்கும். ரொம்ப அருமையான ஒரு கலெக்ஷன். குறிப்பாக தமிழகத்தில் எல்லா பள்ளிகளுக்கும் கொண்டு போய் சேர்க்க முயற்சி பண்ணுறோம். ஒரு நல்ல புத்தகமாக, மாணவர்களுக்கு ஒரு நல்ல வழிகாட்டியாக இந்த புத்தகம் இருக்கும். அடுத்து இனி ஒரு சில நிகழ்ச்சிகள் இதில் தொடர்ச்சியாக நடக்க இருக்குது. குறிப்பாக இது 2 புத்தகங்கள் வெளியிட முயற்சி பண்ணியிருந்தோம். ஒன்று இப்போ வந்துச்சு, இது மிகப்பெரிய ஒர்க்கு, அதனால தான் கொஞ்சம் லேட் ஆகிட்டு இருக்குது. அடுத்து இன்னொரு புத்தகம் துளிருடைய தொகுப்பு, அது 35 வருஷம் வந்துட்டுருது. அந்த தொகுப்பையும் கொண்டு வர முயற்சி பண்ணிகிட்ருக்கோம். அப்புறம் இந்த வெளியீட்டு நிகழ்ச்சி இங்கே மட்டும் இல்லை, தமிழகம் முழுக்க இருக்க 38 மாவட்டங்களில் வெளியீட்டு நிகழ்ச்சி நடக்க போகுது. பல்வேறு கல்வித்துறை அலுவலர்களை கொண்டு கல்லூரிகளிலே இந்த நிகழ்ச்சி நடத்த இருக்கிறோம். குறிப்பாக 38 மாவட்டங்களிலும் வெளியீட்டு நிகழ்ச்சி நடத்த இருக்கிறோம், துளிர் தொகுப்பு வெளிவந்த உடனே. அதே போல் இந்த வருஷம் தேசிய அறிவியல் தின நிகழ்வுகளையும் 1000 மையங்கள் நடத்துவதற்கான திட்டத்தை யோசிச்சுட்ருக்கோம். அடுத்து மாநில அளவிலான, மாவட்ட அளவிலான மேக்ஸ் எக்ஸ்போ, மேக்ஸ் ஒர்க் ஷாப்புக்கான ஒரு திட்டம் இருக்குது. அதையும் முயற்சி பண்ணிகிட்ருக்கோம். ஒரு மேக்ஸ் ஜாத்தாவும் நடத்தலாம்னு முயற்சி பண்ணுறோம். மேக்ஸ்க்கான ஒரு பயணத்தையும் நடத்தலாம்னு ஒரு முயற்சி இருக்குது. அடுத்து இன்னும் கொஞ்சம் கணிதம் சார்ந்த புத்தகங்களை வெளியிடுறதுக்கான திட்டத்தையும் வச்சுருக்கோம். இதையெல்லாம் இந்த வருடத்தில் நடத்த முயற்சி செய்கிறோம். நன்றி, வணக்கம்.
Thank you. I won't go over the entire thing that he went through. I'll just summarize what he was talking about was the fact that since IMSc was taking up a year-long celebration on the occasion of 60, Tamil Nadu Science Forum also decided to take up a year-long program throughout. And what he was talking about was that it started off with January 3, 2022. There was an event at IMSc. And after that, there was a program, online program. This was the Omicron day, so we could not have a physical program. So in January, there was a program on mathematics, a week-long program. And he was pointing out that for mathematics, when they started, they were not sure how many people would come. But as it turned out, this was for teachers. And the registration was exceeded 6,500. So a large number of maths teachers were looking to support. And so this was something that we found. And then for National Science Day, there was a program focused on C.V. Raman. And this was done in more than almost 1,500 places in Tamil Nadu. And then there were mathematics workshops conducted through the year. And these were where they had a little more than 1,000 participants. And these were conducted in Perambalur, Kadalur, Trichy, Madurai, Coimbatore, Salem, Virudunagar, Kanyakumari, Tirupur, Ramanathapuram, Dindigul, and Krishnagiri. So in 12 districts, there were these mathematics workshops conducted. And then there were 25 small books that were released during the year, of which 8 were on mathematics. And then another thing was forming a college teachers forum. And this was inaugurated actually in IMSc. I don't remember now, sometime in August or October or something. Right? And so there is a college teachers forum which is formed, and it has been largely taking up discussions on education policy and education today. That's what is going on. And today, of course, this is a selection of articles from Jantar Mantar, written by persons from the IMSc. And it is also a selection. I think there is a lot more out there, and this is a selection from here. And there is a similar thing being prepared in Tamil and Tulir, and there the release is not in one event, but in every district. That it's planned district-wise, that's what he was saying, in 38 places. That's how it is planned, and the National Science Day events will be taken up in a very similar fashion this year as well. Thank you.
So obviously, I think it's very clear we should congratulate Tamil Nadu Science Forum for the enormous amount of work that they have done in popularizing science. I think I want to, if you can read it through all the lights, we hope this collection will not only enthuse students who are reading it, but also inspire more researchers, especially of IMSc students, to take up the rewarding task of writing high-quality content for interested school students, aimed roughly from 9th to 12th standard for Jantar Mantar and slightly lower classes for Tulir in the fields of basic science, technology, and mathematics, and inspire them to become rational and good citizens and human beings. With that, I would like, this last paragraph I'm reading. This is the last paragraph that I'm reading. I think it probably will not be visible, but there is a note from the director of IMSc, so I guess he will say his own few words. So with this, I think we will come to the actual release of this collection. I particularly want to mention Ahmad Bashir, who was responsible for actually the typesetting, layout, design, and putting together of this entire magazine, who could not be with us here today. Without his help and effort, in spite of many personal problems, he actually raced to get it ready at least by the last day of this event, so we thank him very much for that as well. So I now request Murthy to pick up an issue. And to hand over the first copy to Ravi. So, modern language. It was parallelly released simultaneously to everybody. The final announcement is that this is actually funded by IMSc's outreach activities, this collection. So those of you who are interested, I mean, there are more copies outside. Those of you who think, as I said, this is aimed at high school children. Those of you who would like to read it yourself or to pass it on to children of that age, you are welcome to come and ask me for a copy. And the Tamil Nadu Science Forum is going to distribute thousands of these copies to various school children across Tamil Nadu. So I thank again the Tamil Nadu Science Forum people for coming here and being part of this activity. I'm really happy to see you all here. Thank you very much. One moment. Tamil Nadu Science Forum has also brought out a planner for the year. It's a science planner which includes, instead of Amavasya and Purnima, all the scientific information for the particular day of the week of the month of the year. So I think there are 20 odd copies. So those who are interested can also come and pick them up. Yeah. 20 copy irukudhu illanga? Yeah. So I now request Professor Ravindran to say a few last words and conclude this part of the session.
I would like to welcome the team behind this to happen. Please welcome to this important event. As you know, we are celebrating 60 years of IMSc, and nothing can be as fulfilling as this event, but where we could, showcase the, activities that we could do in connection to outreaching to school children, teachers, and many people actually. So it's one of the important events as far as IMSc 60 celebration is concerned, and we are really happy to sort of make this happen. And I thank the people behind this entire, this whatever work that went into this, getting in time and having it to get released in the important, event of IMSc. Okay, I'm really thankful to all of them who are behind. So I also wanted to say a few words about my experience with this. During RR's time, I got involved in this in a very little way because I was inspired, like Murthy said, I was inspired by the activities by Jam and his team to popularize, science among children and even to, children from slums, because those are the ones actually, as Murthy always points out, catchment area. Okay, so I had, also had gone to places where I had never had been in the past, and after, going there, I could not sleep for a week actually, because it's not that I come from an elite family, I come from a lower middle class family, but even to me, going to such a place, even such places do exist even now actually, okay? It was an eye-opener for me. I went there with one of the faculty members here, Kamal Lodaya, okay? And I was kind of a very small part, volunteer for this Science Forum activities. Arivali Iyakam and Tamil Nadu Science Forum, they had many programs of this kind actually reaching out to this. So it was like an eye-opener for me. I could not eat food actually because when I saw the condition of their living, forget about education, okay? And that is, it's not that it is changed now, it is still continuing actually. So it is not over. It is, every day it's beginning actually, we'll have to reach out to people of different, So it was really fulfilling me to at least to be part of it for, if you compare it to the span that these people spend, what I spend is nothing actually. I just said, because some of you who are here, youngsters, can actually think about, contributing to this. So this is not to just to celebrate something that has happened. It should be a kind of an inspiration for those who are sitting, who are young, who are young compared to any of us here. Actually, I think it's now it's your task, and the ball is in your ground. I think you'll have to really take it up seriously. I think that's what my request here. And I also want to quote one, famous saying by a famous nuclear physicist, Edward Teller. Once he said, actually, science of today is technology of tomorrow. So we cannot forget the fact that all the technology that we are actually enjoying today, communication, this and that, Twitter, blah, blah, all that is actually resultant of something that, that happened almost 100 years before. When quantum mechanics came and things like that. I don't have to teach to this audience what science played actually. So it is important that we'll have to take this to, public, children, people who could not reach to this, kind of thing. Okay. So I think JAM played a very, very important role, not only inspiring people like us, and also inspired, huge number of people actually. So we cannot become JAM. At least we can be a volunteer of JAM. Okay. So at least, I was volunteer for a very short time because of various things. I feel very ashamed that I could not continue like the way he continued actually. But it's okay. But at least we had this opportunity to celebrate this release of this book. It is just a kind of a tip of the iceberg actually. Okay, this is a small thing that we could do. IMSc is really, really happy. In fact, IMSc should be thankful to the Science Forum, JAM, Science Forum and all that for getting us involved in this important activity. Otherwise, we would be, living in a virtual world of doing only science. Okay, so it is an opportunity for all of us to get involved through these kind of activities. And I can also be proud because when I was a student, I had the opportunity to translate from English to Tamil actually. I did not write anything, but I was a translator because I know Tamil. Okay, but some of my seniors used to write and I used to translate because I was not well versed in writing articles when I was a PhD student actually. So thanks for bringing me into this, making me aware of many things, and this event, this being a part of our celebration is actually a proud moment for all of us, and also it is a kind of a event that can actually inspire the young in this audience and continue this legacy of doing and popularizing science among people who could not even think of, doing. Okay, that is very important actually. Thank you. All the best for all of you, and congratulations for doing this wonderful job. So, thank you.
Thanks, Indu. Sure.
Here, I need a copy. Yes. I'll give you more. There are 200 outside. Sorry, you can start.
Professor Naveen. Okay, so again, welcome back. Sorry for the delay. It's my pleasure to welcome Professor Naveen Garg from IIT Delhi for the first scientific talk today, and he's going to tell us about locating charging and service stations.
Thank you. And yeah. Thank you. Thank you for the invitation. I think it's a great honor to be part of these celebrations. I wish IMSc the best. 60 years. I have a cough, and that's expected from people traveling from Delhi, right? So please bear with me when I. This work that I'm going to be talking about today is joint work with two students, Rajni and Dilpreet, and a colleague, Nilima. And I'll tell you a little bit about, this talk is going to be more about algorithms, right? That's the area I work in, and specifically about what are called approximation algorithms. I'll tell you a little bit about what the context is. One particular area of research within algorithms, a large area actually, operations research algorithms is facility location. And a very common setting, let's say, is the following, right? That you are given some clients and you are given some potential facility locations. So in this picture, your clients are these square boxes, and the locations where you can open facilities are these circles. And you're given a metric on these, right? So you're given some distances between these various facilities and these various clients. And now it depends upon what you want to do, right? So you could have many, many different problems, and these all fall into this class of facility location problems. So one problem that we'll be interested in this talk is what is called the K-supplier problem. Okay, and that is just the following, that you want to open some K facilities. I give you this number, K. You want to open K facilities, and in such a manner such that you minimize the maximum distance of any client to the facilities that you opened. Okay, so think of these as, these clients are locations of people who, let's say, access a public distribution system, and you want to open some ration shops, right? And so what would be good places to open ration shops, given that you are allowed to open, let's say, only K ration shops, such that the maximum distance any client has to travel is as small as possible. Yeah? So in this example, if K were 2, that is, you had money only to open 2 such shops, then if you place them at those 2 orange spots, then you would incur a cost of 9. What does that mean? That means that the maximum distance any client would travel would be at most 9, and I believe this client will travel 3 and 4, 7 and 2, 9 to reach there. Everyone else will travel less than 9, right? So this may or may not be the optimum solution, but I think it is, but you can check. There is also another problem which is called the K-center problem. And I think of it as, you're given some points in a plane, and you want to find out where, once again, the same things, but you have no restriction on where you can place the points, right, where you can open your facilities. And then the objective is still the same. You want to open the K centers in such a manner such that the maximum distance any client has to travel to the nearest facility is as small as possible. So this is classic facility location. And we said, well, everyone is talking about charging and electric vehicles these days, so why not see if we can produce, we can look at some of those problems coming from that domain. And that's what this talk is about. So that's where the charging stations come from, and I'll come to that in a short while. So now, earlier, our clients were these points, right? So we said people, houses of people. Now suppose clients were paths. Okay. Let's create a story. So suppose, you follow a certain route from work to home every day, right? So That's the path you traverse. And now you have these path information for many, many users. And let's say you are a service provider. Let's say you have petrol pumps. You want to open some petrol stations. Okay? Now, how should you place these petrol stations so that ideally you would want to place the petrol stations in such a manner such that no one has to deviate from their path to access a petrol station, right? But suppose you did not have the money to set up so many petrol stations, then it would make sense to look at the objective of minimizing the maximum detour one would have to make. Yeah? And so with that objective, so this is the setting now. So you're given these source destination pairs. So I'm going to be using these colors. So red color, and I can't use the pointer, but that's okay. So, or I can just do it on this. Right? So the red, there is this red path, and there is a green path which goes like that, and there's a blue path which goes like that, and so on. Oh, sorry, this blue path went like that. So these are the various paths, and now question is, how should you place two petrol stations so that the maximum detour any client has to make is as little as possible. Okay? So, right. So if we were to open once again these petrol stations at these two places, the orange blobs, then note that the yellow path would not have to take any detour. The green path would not have to take any detour. The blue will not have to take any detour either. The blue path, I do not know if you can see those colors, but the blue path is going like that, so one of the petrol stations is on it. The purple will not have to take any detour, so the only path that needs a detour is the red path, because there is no petrol pump on the red path, right? The red path is going like that. And so this guy will have to come here, go back here. So there's a detour of 3 units, or a total detour of 6 units to access a petrol pump. Question, Meena? Yeah. Oh, you can't see the cursor. Yeah, the laser pointer does not seem to be. Can you see the laser pointer? You can, okay. So the yellow path, this is the yellow path, right? No detour needed there. Green path, no detour needed because there is something there. Blue path is this one, right? So again, there is a petrol pump on the blue path. On the purple path also there is a petrol pump. It's only the red path which is sort of, which is without a petrol pump, and there is a detour needed, and the detour is 3 and 3, 6. So we can count it whichever way you want, only the distance or twice the distance, it doesn't matter. So we're counting it twice the distance, so the maximum detour needed is 6. So that's the question. How would you, so given these paths, right, how would you place these K facilities so that the maximum detour is as small as possible? So a natural question to ask is, there's so much literature available on facility location problems. Why not use some of those techniques to solve this, right? What's the challenge? And the challenge is actually, in all of this work on facility location, you assume that you have a metric. And we are also assuming that there is a metric on the points, right? But here, so one other thing that gets used very often is this inequality, which says that, well, if I have clients I1, I2, and some facilities J1, J2, then by triangle inequality, it should be the case that the distance from I1 to J1 is less than the distance from I1 to J2, plus the distance from I2 to J2, plus the distance from I2 to J1, right? So this is just whatever, quadrilateral inequality, whatever you would like to call that, okay? Now note that, okay, so first you will have to define, you'll have to think of what is the distance of a client from a facility, right? Now client is a path. So what is the distance of a path from a point? A facility is a point. Well, it's obvious to, a natural definition would be, let's look at the nearest point on the path, and let's define that as the distance. But when you do that, this inequality goes away, right? You can't say anymore, and this is a very simple example to show that here on the right. So you have 2 paths, I1 and I2, and I have 2 clients, J1 and J2. sorry, I should have, okay, I think I interchanged the clients and the notation for clients. But nevertheless, you have two paths, I1 and I2, and two clients, J1 and J2. And J1 sits on I2, and J2 also sits on I2. And J2 also sits on I1. Okay? So the distance of J1 from I2, the distance of J2 from I2, the distance of I1 from J2, all of these are 0 because they sit on them. But the distance of J1 from I1 is non-zero, right? And so, most of the machinery that has been developed for facility location problems, goes out of the window. We can't use it anymore. And what we can do, so we were exploring this and to see what are the various things we can solve in this setting. And there's a very simple algorithm you can imagine. For trees, it's, most problems are very simple, and that's the case here as well. Again, so what is the metric now is the tree. I give you these clients. I give you the source destination pairs, and I give you the path. And I say, find the smallest number of, given k facilities that you can locate, what's the smallest detour? And we turn this around, we say, let's first guess the value of the detour, right, that you need to make. So suppose my guess is D. So with this value of detour, I'm going to, fairly obvious thing. So you would, let's run through the algorithm. You would find the least common ancestor of each of these source destination pairs. So those are your least common ancestors. And now you're going to take the one which is furthest away from the root. So that would be, so that would be this one here, right? This is the one which is furthest away from the root. And from here, you are going to go D units up. So that's 2 units, D is 2. So you're going to go 2 units up, and you're going to pick this facility. You're going to open a petrol pump here. Why? Well, this is definitely going to cover this, right? Because this is the least common ancestor, and you're going only 2 units up from here, right? And in some sense, you need something below this to cover this pair, right? And so you've sort of taken the furthest thing closer to the root, and you just repeat this. And one can argue that this works. So, so you will, once you pick that, you will remove everything that it covers. Note that it covers both the blue and the green paths, right? Because it also, but it doesn't cover the red path, right? Because the red will have to take a detour of 3 to get there. So you remove blue and green. They go out of the picture. And now you repeat the same thing for red. For whatever is remaining, and you will end up picking 2. And if you had made the right choice for D, then this will give you the minimum number of facilities that you need to open. So what happens when the metrics are arbitrary? It's not a tree metric. So remember, just to recall, you have these paths, right? And you're given a number k, and you want to find out how to locate these facilities so that the maximum detour that any client has to take is minimized. So if L is the longest path, let's say in terms of the number of edges, right? If L is 1, then this problem is like the vertex cover problem, right? L is 1 means edges, so each client path is just an edge. And what is it that you want to do, right? So you're given a bunch of edges, and you want to find some vertices which cover all of these edges, right? Which hit one end point of each edge. And that's like vertex cover, right? So the problem of checking if there is a detour of size 0 is the same as checking if there is a vertex cover of size k. And so it's NP hard, right? Even for L equals 1. And what we can do is we can give an algorithm which returns a solution of value 3 times op plus L. Very weird number, but tight, right? So you can't do anything better than this, provably. Assuming P not equal to P. So I'm not going to say it's not a very difficult algorithm. I'll go on to the charging station business because I did not get to that yet. So we think of this previous problem that I just talked about more as locating service stations, right, or gas stations. Now, another interesting problem in the same domain is the setting of a charging station, right? So now you have electric vehicles. And then every electric vehicle comes with a certain range, right? What is the distance it can travel on a full charge? Okay, so now we're thinking of, we're given these source destination pairs, right? I have an electric vehicle, I work at IMSc, I live in wherever, and I need to be able to go every day from home to work, right? And for now, I'm assuming I can take any path whatsoever. I just want to be able to reach home, right? And my vehicle has a certain charge, a certain capacity, and I should be able to drive in such a manner such that I never run out of charge. So we are going to assume that we are given these source destination pairs, and we are given a metric on the terminals, again distance metric, and we'll assume that there is a range of b kilometers that any car can travel, an electric vehicle can travel. And we want to open the charging station so that every car can reach its destination. And we will assume that when a car starts from its source, it starts with a full charge, right? Because if it's empty, then what do you do, and so on and on. So at night, everyone charges their car fully, and so next morning when they start, they can start with a full charge. And note here that the paths are not specified. We are only given the source destination pairs. So in particular, just as an example, look at the picture on the right. So if, let's say this is the source here. Okay, so let's say the source is the top red square, and that's the path I want to follow. Of course, here we are not given the paths, but suppose that was the path I wanted to follow. I had a range of 200 kilometers, then I need a charging station at the green place or earlier for me to be able to make this journey. And with just that one charging station, I would have made this journey. So if I had just one single path, of course, I can solve the problem. But now we have many sourcing paths, and I want to identify the smallest number of charging stations I need to be able to to be able to service all of these customers. Yeah, I'm making it sound like it's all very important and useful. It's not, right? It's all just fun. So, but these are interesting problems that we thought of from a facility location perspective. Okay, what does the optimum solution look like, right? So this is where, okay, so what I'm going to do is, so we'll have these, remember we have these source destination pairs, right? So we'll think of them as these square boxes. So the red and the red, that's the source and destination for a particular vehicle, and so on and on. And now if you look at where the charging stations are placed, so suppose you computed the optimum solution, right? What does that solution look like? So I claim the following, right? So suppose you took this metric that you had and retained only, you kept an edge. So let's say you create a graph and you kept an edge between two vertices if the distance between them is less than b, which basically means you can go from one vertex to another. Okay? So we kept only such edges. Now the optimum solution is a set of vertices O. So the optimum solution would look like these vertices, these circles in the picture, right? This is what it will look like. Let's see why. So what property should this have? So this should be some kind of a connected subgraph. We'll assume it's a tree. And it should be such that in each connected component, so every pair appears in a connected component or the other, right? So if this is where the thing was opened at those places, then I claim that the blue guy can go to the blue guy. The blue vehicle can go from its source to its destination. How would it traverse? It will start from there. It will go there. There's a charging station opened here, so on and on. And each of these edges of length less than b, so it will follow that and reach there. Long path, but it will do that. It can do that. And so our problem now is the following. I give you, So what is it that we want to do? We want to compute something like what's called a Steiner forest, right? I give you these pairs. I want to compute a subgraph which has the smallest number of nodes in it, because that's the number of charging stations I need. And in every connected component of that subgraph that I compute, every pair should appear in one of the connected components. So that's a Steiner forest problem. And a small technical point, these are not just Steiner forests, these are what are called full Steiner forests, right? A terminal cannot be an internal node here, right? So imagine, so what's a terminal? The terminal is the home of some person, right? Now, if that's an internal node, what does that mean? That means that someone else comes to your house every morning to charge their car, right? That doesn't make sense. So these terminals have to be the leaves of whatever structure you build. And actually, it's an important technical consideration because this makes the problem much harder. So these are called full Steiner trees. So what we want to do is we want to compute full Steiner trees. And I'll tell you a little bit about this, and this might not make a lot of sense this slide might not make a lot of sense for people who do not know some of this stuff, but bear with me, I'll just quickly go over it. So if I have to compute Steiner forests with the minimum number of nodes in it, there is a log K approximation that is known, and it's possible to do that. But as I said, we want to compute Steiner forests which are full Steiner forests, and that becomes a much harder problem. It's equivalent to what's called the group Steiner tree problem. Actually, group Steiner forest, node weighted, and nothing is known, right? Or the only algorithm known is some quasi-polynomial time algorithm, which has a polylog approximation. But let's skip that. Let me show you one algorithm for this in the next 5 minutes. And here what we are going to do, so we are saying that it's very hard to solve this problem, or the best approximation we can think of is it'll take quasi-polynomial time and polylog. It's not very interesting. Let's do a little bit. Let's do things differently. Let's change the problem a little bit, right? It's a standard thing we do when we can't solve a problem. We change it, right? So what we are going to do now is we are going to increase the range of our vehicles, right? Almost cheating, but that's the best we can do. So what we are going to say is, my vehicle, I'm going to develop a solution where I am allowed to travel twice as much as the best solution, right? So I'm going to look at the best solution with range B and compare it to a solution that I develop with a range twice B, okay? Okay, how do I do this? So we'll walk you through this. So this was, let's say, the graph and the metric that was given to me and the pairs and all of that. So we said, we said this earlier, we'll take a metric closure, which basically means we'll add all edges by computing the shortest path distances between the points. And then we will only retain those edges which have length less than or equal to B, right? You understand why I'm insisting on edges of length less than or equal to B, because those are the only edges we can use. If an edge is very long, much larger than B, I cannot use that edge. Or even the optimum solution cannot use that edge. So I do that. I have chosen B as 4, and I took that earlier graph that I showed you. I took the metric closure, and I was left with these edges. Right? The dotted edges are those that I added because of the metric closure. Now I'm going to compute a Steiner forest in this, a node-weighted Steiner forest in this graph that I have. Okay? So a Steiner forest which has the smallest number of vertices. So let's say these are the dark edges that I get. So I'm going to now throw away all the other edges so that you can see it very clearly what we have. And now you see what the problem is, right? So here, and I hope I can, so here we have a vertex here, right? This red one here. So this is a Steiner forest. As you can see, there is a path between every pair of vertices, right? So I can go from here to here by following this path. Ignore the colors because the colors were coming from the earlier setting, right? But if these were the stations that were set up, 1, 2, 3, 4, 5, 6, and 7 charging stations that were set up, then I know that this edge is of length less than b, this edge is of length less than b, this is of length less than b, this is of length less than b, and so on, and I can go from here to here. Looks fine, except that we have this problem that this is not a full Steiner tree, right? So note that this might be someone's home, what I said earlier, right? And how can I put a charging station there? So we want to get around that problem, and so what we do is, the standard idea is that if this is of length, so I short circuit, right? I add these edges, which are of length 2b now, okay? And I will then remove one of those edges. So I got now, as you can see, a full Steiner tree. Can always be done, right? So this is a full Steiner tree. None of the terminals are any internal nodes in this tree. So that's where the 2b comes from, right? We said we have a range of 2b. Why do we need this range of 2b? Because we want to say that you can travel from here to here. Actually, this edge has length, does not have length less than b. This edge plus this edge had a length less than b, and so this edge has a length at most 2b. Okay, so I am almost out of time, so I'm going to stop very soon. But we took this further, and I'm not going to show you the whole algorithm here. We took this further, and we said, okay, can we get a constant approximation, right? So still we're getting only a log approximation. Can we get a constant approximation? And we can if we allow a range of 4 times b, right? And this is a bit weird, right? So you saw the reason for 2b. I do not have a simple argument for why 4 times b suddenly you can go from log to a constant. But it's interesting that, you know, if you increase your range of vehicles in this manner, you can get a constant approximation. And I have nice slides for it, but I don't have the time, so we'll skip that. Okay. Just to tease you a little bit, let me. So with that, that brings me to what else we did. So that's interesting, right? So you can set up these, and what value does it have? What meaning does it have? I'm not particularly sure. But you can, by increasing the range of these vehicles, get better and better approximations. So we also looked at, suppose, so here in this previous problem, I told you we were just specifying the source and the destination. But suppose I also tell you that, you have to follow this path, or the vehicle is following this path, right? Earlier, there was no path that was specified for the vehicle. It could take anywhere till it could get from the source to the destination. Now, it had to take a certain path, and, it was not allowed to take any detour. Then, again, it's hard to get a better than a log k approximation. And we can extend this to show that you cannot even get a log k by alpha approximation if you're allowed a range of alpha times b. So it's a minor result, not a very great thing. So in this particular, so why am I putting this slide? So here for this particular problem, it shows that, this earlier you saw that increasing the range suddenly leads to a significant improvement in approximation ratio. That doesn't seem to happen here. You increase the range by 2, your approximation ratio will reduce by a factor of 2, not a significant drop as we saw earlier from log n to just a constant. Okay, so I'm going to stop now. So what I've shown you is how to, to this new set of problems that we sort of stumbled upon, locating these charging stations. We do not know of a lot of prior work on this. Much of the work has been done in the experimental community where they have some heuristics which they run to, but not in the TCS community. The unsatisfying part is that we are only able to obtain these pseudo approximation algorithms, right? That we have to increase the range of the vehicles to get any meaningful numbers. But getting true approximations seems like particularly hard in this setting. One other thing we've not considered is that, we said, I give you source destination, you could follow any path, but that means that you could also be taking a very, very long path, right, to get to your destination. And so is there a way of, limiting the length of the path and still obtaining meaningful approximations? When you start doing that, you hit these, these bad bounds, right? Everything seems to be polylog, at least polylog, and not a constant approximation. So that's all. This was more, this was work we did, during the pandemic, and somehow with the general, gloom around, the kind of results that we came up with were also not very pleasing or happy, but nevertheless, I thought I should talk about it a little bit to see if there are some fresh ideas I can get on, how one could look at different ways of addressing this problem, or whether there are variants of this problem one could come up with which would make interesting topics for research or discussion. Thank you.
Thanks a lot, Professor Garg, and thanks for keeping time. Please wait, we have a token of appreciation.
Okay. Okay. Thank you. Oh, sorry.
So for the next talk, I would like to welcome Professor Rukmini De from ICT STIFR Bangalore campus, and she's going to tell us about minimal surfaces.
Okay, thank you. I would like to begin by thanking the organizers for inviting me for this great celebration. It's really an honor for me to be here. And so today I'll be talking about minimal surfaces. I'll just put this here. Today I'll be talking about minimal surfaces because when we are children, we have always played with soap films and soap bubbles, and without knowing that there is such beautiful mathematics behind it. And some of you already probably know what I'm going to talk about, but and also it's not going to be very rigorous because I'm trying to address a mixed audience. So I'll be talking about this beautiful surfaces. So before we start, topology of compact oriented surfaces compact-oriented surfaces are classified by their genus. The genus 0 surfaces, are these spheres, right? Or ellipsoids, or these are the genus 0 surfaces. These are genus 1. This is triple torus, so genus 3. So to a sphere, you keep adding handles, and that kind of gives you the genuses, the holes through these. These are genuses. And there's a beautiful formula of Euler which says if you can divide it up into how do I go back? Oh. Yeah, so if you can divide up the surfaces into faces, into vertices, I mean you divide it up into faces, certain number of vertices and edges. So then V minus E plus F is equal to 2 minus 2G for a compact oriented surface. So if you can, for example, the sphere, if you can break it up into, like for example, a cube. Cube is actually topologically the same as the sphere, and if you calculate V minus E plus F, you will get 2 minus 0. And similarly for all the Platonic solids. For example, for the octahedron, tetrahedron, octahedron, dodecahedron, icosahedron, if you calculate V minus E plus F, you will find it's just 2, right? And for the plane, for a triangle, you will see V minus E plus F is 1. And Mobius strip, this is, and then I just wanted to, show an example of a non-oriented surface with a boundary, and this is a Mobius strip, and it comes up in minimal surfaces a lot. So this is one thing. And so that was topology. What I was talking about is when you don't really care about the, you don't care about continuous deformations, right? Like you can squish a ball into a ellipsoid and topologically they will be equivalent. But now we start to care about the details a bit. So that is geometry. So we talk about lengths of curves on surfaces, area of the surface, Gaussian curvature, mean curvature, etc. Sphere and ellipsoids, though topologically they are equivalent, they are very different in this sense. For example, the sphere is totally symmetric while the ellipsoid is not. So here geometry plays a role. So minimal surfaces is more about geometry rather than topology, and we will see very soon some pictures of those. So parameterized surfaces in R3. So in our entire discussion we will be using parameterized surfaces in R3. So x in this bold is x of uv, y of uv, z of uv. uv are two parameters which are locally describing the surface. Okay. For example, if you take z is equal to tan inverse y by x, this is actually a surface called the helicoid, and you can parameterize it in many ways. For example, uv tan inverse v by u, or r cosine theta, r sine theta, theta, right? But then we can also introduce a very novel parameterization in terms of complex numbers. So you take zeta to be u plus iv, and you can just write x of uv as x of zeta zeta bar, y of zeta zeta bar, z of zeta zeta bar, where x is of the form minus half imaginary zeta plus 1 over zeta, y is half real part of zeta minus 1 over zeta, and z is minus pi by 2 imaginary ln zeta. If you solve this, you will get exactly this equation, z is equal to tan inverse y by x. So why am I talking about this kind of parameterization? And okay, the parameterization fails for zeta is equal to 0, as you can see. So this kind of parameterization holds because the helicoid is actually a minimal surface. So we will see parameterizations like this occur, like x is real or imaginary part of a holomorphic function, y is real or imaginary part of a holomorphic function, z is a real or an imaginary part of a holomorphic function. They are what are known as harmonic functions. Okay. So this kind of parameterization occurs if the surface is a helicoid. So that's, I'll come to that. So what are minimal surfaces? We'll be talking about these surfaces which appear in nature as idealized soap films. They are stationary points of the area functional. Locally they are area minimizing, or a saddle point of the area functional. So you can see these soap films, we have played with these as children, right? So and the mathematical property is the mean curvature is 0 at every point. So for all those who know what about this curvature, the principal curvatures, so if K1 and K2 are the two principal curvatures, then K1 plus K2 equals to 0. And if K1 and K2 are non-zero, then you know the principal curves, the principal lines of curvature curve in opposite directions. If one of them curve like this, the other one curves like this. So it's actually a saddle at every non-umbilical point. And they have negative or 0 Gaussian curvature. Umbilical points are where the Gaussian curvature is 0. Soap bubbles, however, are not minimal surfaces. They have constant mean curvature at every point, not 0 mean curvature, non-zero constant mean curvature every point. And they are actually part of this huge topic called integrable systems. The constant mean curvature surfaces are very difficult to, they are much harder to describe. The sphere is the sphere, cylinder, these are very simple examples. Okay, back to minimal surfaces. For example, this helicoid and the catenoid, they are actually related. Later on we will see actually they are related. And so this is the helicoid, this is the catenoid. Catenoid is got, you take a catenary, revolve it about this axis, you will get a catenoid. And helicoid you have seen as spiral staircases. And this is the NAPA surface you have seen in potato chips. This is the shape. And this is another type of NAPA surface. These are the shark surfaces. This also will come up in my talk later on. This is the shark's second surface. This is the shark's first surface. And again, they are also related in some ways. I mean, we'll see. There is a way of going from one to the other through a family of minimal surfaces. And then there is this is the genus 1 Costa surface. It's an immersion of a torus with 3 punctures. You take a torus, take 3 punctures, and you can immerse it in R3 using some number theoretic functions called Weierstrass P functions, and this is how it looks like. So believe it or not, there is only one genus and there are 3 punctures. The 3 punctures have opened out as 3 ends, like these 3 ends. And then there is the Riemann staircase. This is the genus 1 and multiple genus helicoids. And this is a triply periodic minimal surface which appears in crystallography. So sometimes since the audience is diverse here, like equipotential surfaces in crystallography are minimal surfaces often. Like if you have crystals and there could be a surface through those molecules such that there is no force on it, right? You can imagine a surface such that all forces are like balanced on that surface. That turns out often to be a minimal surface. So in crystallography also these appear. Okay, Plato's problem for the lay person. So given a small closed wire, if you dip it in soap solution, is there a soap film spanning it, and if so, how many? So Douglas gave an answer to this, Jesse Douglas, he got the first Fields medal for this. Douglas gave answer to the mathematical formulation of this question. He said yes, and subsequently this has been an active field of research. And the question of how many minimal surfaces span a given curve has been studied by Tromba using catastrophe theory. So here I was telling you about the Mobius strip. So you have a Mobius curve, you dip it in soap solution, you can get these kind of surfaces. This is one type, this is a second type. Okay. So actually the number of, if you dip a soap, I don't know if you have played with wireframes and soap solutions, if you dip it in, if you dip a wireframe in soap solution, you may not get a unique soap film spanning it. There could be various soap films spanning it. So let us go into little bit into the mathematics behind it. So if you can write your surface locally as xy phi of xy, then the mean curvature 0 equation is actually quite a complicated PDE. 1 plus phi x squared phi yy minus 2 phi x phi y phi xy plus 1 plus phi y squared phi xx equals to 0. It's a complicated PDE, but the nice thing about this is in isothermal or conformal parameters, if you choose your UV properly, you can write it as x of uv, y of uv, z of uv, conformal parameters, and in these coordinates just the equation, the x, y and z just becomes Laplacian of x equals to 0. So in each coordinates, each coordinates become harmonic functions in these special UV coordinates. So finding the conformal parameters may be difficult, but if you can get conformal parameters, then this complicated equation just becomes harmonicity of the coordinates. So this is I have written here what is the conformality condition. Norm xu equals to norm xv, and XU, XV are orthogonal. Okay. So that kind of harmonicity of coordinates means you can relate it to, you can immediately relate it to complex analysis, because real and imaginary part of holomorphic functions are harmonic. Okay. So, and also from that it follows that complete minimal surfaces cannot be compact. So, for example, a torus can never be thought of, never be immersed into R3 as a minimal surface. You have to remove certain points. For example, torus with 3 punctures, as I showed. Okay. So, and then the most general solution of that equation is zeta is u plus iv, zeta bar is u minus iv, then you can write x of zeta zeta bar in this way, y of zeta zeta bar in this way, and z of zeta zeta bar in this way, where f and g, f is holomorphic, g is meromorphic, such that fg squared is holomorphic, and so basically what I am saying is holomorphic is it does not depend on w, it does depends on w, it does not depend on w bar. Okay. And in that case you can actually choose your favorite f and g such that f and g are, f is holomorphic, g can be meromorphic, but fg squared is holomorphic. In that case you can construct, this is going to be always a minimal surface. So, you can take your favorite one, okay. Favorite f and g, only restrictions are these. So, there is another way of writing it. In a neighborhood of non-umbilical point where the Gaussian curvature is non-zero, any minimal surface can be represented in terms of a non-vanishing meromorphic function. You can actually choose your favorite meromorphic function, and meromorphic function are holomorphic, but they can have poles, they are allowed to have poles. Okay. So, they depend only on W, but they can have poles. So, yeah. So, any minimal surfaces can be represented in terms of one non-vanishing meromorphic function like this. Again, this is always going to be a minimal surface, and you can pick and choose your R. For example, R is equal to 1 corresponds to the NEPA surface. This corresponds to the catenoid, this corresponds to the helicoid. So, all you have to do is pick your favorite R and perform the integrals to get your minimal surface. Okay. I am not going to go into all these details. So, finally, I wanted to tell an interesting fact which me and my collaborators have found, how Ramanujan's identities are also coming in minimal surface theory. So, here this is a Scherk surface type 2 and this is type 1 Scherk surface, right. Okay, so here I have actually performed the integrals and shown. So, this was for the helicoid. After performing the integrals, you get that representation I was talking about initially. Oh, sorry, before going into Ramanujan identity, there is a beautiful fact that there is a whole family isometric deformation from the helicoid to the catenoid such that this at every stage it is a minimal surface. So, you see the topology is changing. Here the helicoid has a very different topology from the catenoid, but you can still deform, go from one to the other through a family of minimal surfaces. So, that is why this is called the conjugate of this. In some sense they are actually conjugates of this. So, I am not going into the theory. Similarly, this one and this one, actually there is a way of going from one to the other through a family of minimal surfaces. I have not shown the picture, actually I do not have the picture of that. So, okay, finally, how much time do I have? 10 minutes, okay, good. So, a geometrical interpretation of an identity of Ramanujan, actually Euler-Ramanujan I should put. Euler also used to know this. So, tan inverse tan h y cot x is summation k goes from minus infinity to infinity tan inverse y by x plus k pi. Okay. So, this is a Euler-Ramanujan identity. This is one of the identities. But the amazing thing is, this left-hand side is a height function of a minimal surface. Z is equal to tan inverse tan hy cot x is one way of writing this red. Oh, maybe I have the picture later on. This one. This one can be represented like that. The height function is tan inverse tan h y cot x. It's the Shark's first surface. And these you already, tan inverse y by x you already know is a helicoid, and these are just shifted by k pi. So I have shifted an array of helicoids and added the height functions, okay, and I got a minimal surface, which is not to be expected at all from a very nonlinear complicated equation, right? So this is what one of the identities give. And this was used by a condensed matter physicist and his collaborator Randall Kamian of UPenn. So we have used this for some other things. And recently also, me and my collaborators, we have found finite decompositions. So for example, z of xy is equal to ln cosine y by cosine x. This is this one, sorry, the other Shark surface, the one with tunnels, what was it? This one. This is the one which is given by z is equal to ln cosine y by cosine x. Okay, and that also is part of a Euler-Ramanujan identity, because this is the identity of Ramanujan. Okay, cosine of x plus a by cosine a is this. So if you take ln on both sides, you take x plus a to be y and a to be x, then you can get this kind of an identity, and this is the height function of that tunnel-like minimal surface, right? The Shark's second surface. And what we did was to cleverly rearrange this, just a clever rearrangement of these sums. These sums, instead of k goes from 1 to m, we just write it as k np plus m, and we could rearrange it to get that there is a finite decomposition also. So z of x comma y, which was this, is summation m goes to 0 to n minus 1, z by x by n minus some constant, y by n minus some constant. So up to translations and scalings, what we got is Shark's first surface can be decomposed as finite sums of height functions of the same type. These are not exactly minimal surfaces, but they are scaled ones. So if you just took 1 over n here also, then it will be a minimal surface. So if you look at the minimal surface equation, if you scale x by x by say alpha x, scale it by alpha, y also is scaled by alpha, z also is scaled by alpha, the equation remains invariant. So almost minimal surfaces which look like the Shark's second surface, so the height functions can be finitely decomposed. So, and the other thing which we are working on is how close this so Douglas's work shows that there is a very interesting interpolation problem. So you can ask, given two real analytic curves or just Jordan curves, say simple curves, okay, then how close should they be so that there is an interpolating minimal surface. Okay, so supposing you have two wireframes, I am dipping it into soap solution. If you put them very far apart, energetically it will be more suitable for it to have two independent disconnected parts. But if you bring it close together, then actually energetically it's better to have it will prefer to have an interpolating minimal surface. So we actually used some
inverse function theorem in infinite dimensional setting, and Beerding-Schwarz problem, so to show how close they should be. And secondly, we are also trying to work on maximal surfaces in Lorentz-Minkowski space where this Plato type problem has not been solved, and we could get this kind of interpolation by those maximal surfaces using the same method. So it's only existence results so far, but we are trying to get many examples. So that is this thing. And so if anybody wants to get into minimal surfaces, there are very beautiful work. So first is Manfredo Docharmeau's Differential Geometry of Curves and Surfaces. That is a very basic, beautiful book on curves and surfaces. Then Osserman's book of Survey of Minimal Surfaces, Dierkes and Hildebrand, Kuster and Bolrav. Then Nietzsche, Witham, Ramanujan, Lopez, all these that are very, so this is what I was saying, the maximal surfaces in Lorentz-Minkowski space, if anyone wants to get into that. And so me and my collaborators also have a lot of work on this direction. And this is the one I was talking about, finite decompositions of height functions, not only of minimal surfaces, maximal surfaces, Born-Infeld solitons, time-like minimal surfaces. And so what we find is they have similar kind of nonlinear equations, but you can still decompose the height functions into scaled and translated versions of itself. So solution, yeah, so that's it. Thank you.
Thank you, Professor Dev, for nice talk and interesting pictures. We have a small token of appreciation.
Thank you so much.
Sorry. Oh, yeah, no, he's here. Okay, he probably didn't, he's here, he's somewhere here.
Isn't his talk before me?
No, your talk is now. Okay, so for the next talk, it's my pleasure to welcome Sushmita Venugopalan, my colleague from IMSc, and she's going to tell us about counting curves tropically.
Thank you for the invitation. Just a second. Okay. Okay, so let me start by asking the only question in this talk which you can answer. If I give you two distinct points in R2, the plane, how many lines are there through the two points? So it's one line, right? So, and this analog, you can ask analogous questions in complex space, C2, and now we are talking about complex lines. And again, the geometry is the same, and you just get one complex line passing through 2 points in C2. And let's make it slightly more complicated. So instead of C2, let me talk about complex projective space in 2 dimensions, which you may think of as like a compactification of C2, in which the lines at infinity are at you add lines at infinities, and they are kind of at par with other lines in C2. So the same thing what we observe in C2 continues to be true in complex projective space also, which is CP2, but I'll drop the field and just talk about, refer to it as P2. The answer to the first 3 questions is just one line through 2 given points. But so the title of my talk is Counting Curves Tropically. So my first job is to just tell you what I mean by counting curves. So that's where I'm getting to here. So typically when I'm talking about counting curves, I'm talking about counting parametrized curves. So so in the case of projective space, lines should actually be thought of as spheres like compactified lines. So complex line is a C, and when you compactify it, it's an S2. So when you parametrize such lines, these are actually linear maps from P1 to P2, which have that form in homogeneous coordinates. Okay, so we are talking about parametrized lines. So then we also have to account for the fact that, you know, reparametrizing the domain should not give you a different line. So we need to take the space of all linear maps and mod out by domain automorphisms, and then look at these objects and then constrain them to pass through two fixed points. So in some sense, this problem is same as the preceding three problems which felt more intuitive. It's only that I'm parametrizing the domain and modding out by domain reparametrizations. Okay, so so that's counting curves in degree 1. And we can ask the same question in for higher degree. So if I look at degree D maps, what I'm really asking for is those linear maps there get replaced by degree D homogeneous polynomials. So those P0, P1, and P2 are homogeneous polynomials of degree D. And again, I mod out by reparametrizations of the domain and require that the image contains, instead of two fixed points. So now when I'm talking about degree D polynomials, it has a whole lot of coefficients. So there is the degree of freedom is much higher. So to make sure that we get isolated solutions, you know, like if there is a solution, you shouldn't be able to kind of move it and get a whole continuous family. In order to ensure that the set of solutions is unique, you need to fix 3D minus 1 points and constrain your map to contain those 3D minus 1 points in its image. And if you do that, the answer is a discrete number, and we denote this number by ND. And in the first, N1 and N2 are 1 is elementary. N1 is 1 is what we saw in the last slide. And N2 is 1 is the result that, which is kind of a classic elementary result, which says that there is exactly one quadric passing through 5 generic points. So if you start doing some algebraic geometry, that's like one of the first things you see, and it's something you can actually calculate by hand. If you, you know, just work with those, you take quadratic polynomials and constrain them to pass through 5 generic points. But 3 onwards, it gets complicated. 3 was computed in 1848, 4 took more time, 1873, and after that people were stuck until 1994, when Kontsevich gave a recursive formula for ND, kind of revolutionizing the field. Okay, so this field, so this problem of counting curves in P2 can be extended to counting curves in other manifolds or other projective varieties. And you know, the study of these problems is done under the name of Gromov-Witten theory, and these are called Gromov-Witten invariants. And one of the biggest problems you encounter when you start counting curves in spaces which are more complicated than P2 is that that curves that should not exist for index reasons actually exist. Like even in the P2 case, if you take points which are not generic, so suppose you take all your points lying on one line, then you get like a whole lot of curves which should not exist generically, but so in some sense, so you can kind of assign like an index to every curve, and if the index is negative, that curve should not exist, but they nevertheless exist. So for that reason, Yeah, so that's what makes the question somewhat complicated. And in symplectic geometry, which is the field I work in, the way we deal with this problem is to perturb the complex structure. So, so essentially, these maps that we are talking about, these maps U, which I mentioned in the previous slides, these are solutions of a partial differential equation, which says that these maps should be complex linear. So that complex linearity is a partial differential equation, and perturbing the almost complex structure involves introducing a perturbation so that only the ones which you expect to exist actually exist. So that's how symplectic geometers think about curve counting problems. Anyway, so much for abstraction. Let me actually get down to some pictures now. So I'm, from here, I kind of, this is like a next section of the talk where I talk of, yeah, you know, if you're zoned out with all this technical nonsense, can come back. So I'm going to talk about something called tropical curves, which don't look like curves at all. These are not you know, maps or functions or anything. They are literally combinatorial object called graphs. So what are tropical curves? So we are talking about tropical curves lying in R2. So these are graphs which lie in R2 and whose edge slopes. So each of these edge has a rational slope, so a rational element of R2 associated to it, and those numbers add up to 0 at any of the nodes. So I'm hoping that that is obvious from the picture, because in most of the nodes my slopes are just -1, 0, 0, -1 and 1, 1. So those add up to 0 at the junctions, and there's just one example where there's a slightly different slope involved. So that's what these tropical curves are. And another condition is that their infinite edges have these fixed slopes. So, that's again something you can verify in all three pictures, that there are three kinds of slopes that occur for the infinite edges. So infinite edges are edges which just have one vertex and are just going out to infinity on the other side. Questions? So it's not slope in the conventional sense. It's you take the slope and associate a z square, a tuple of two integers to it, which is in the primitive form, making sure there are no common factors. So that's the slope. So I have labeled these some of the edges by their slopes. I have time for one more question. Okay. So if, and also notice that the number of infinite edges in each of these three directions determines the degree of the tropical curve. So the degree, again, that is something that is obvious from these three pictures of a degree 1, degree 2, and degree 3 tropical curve. Okay, now the remarkable thing is that if we do the same thing with tropical curves, if you fix 3D minus 1 generic points in R2 and you look at degree D tropical curves passing through those fixed points, then that set is going to be a discrete set. It's not a continuous family, similar to what we saw in curves earlier. And this number, the number of degree D tropical curves through 3D minus 1 points is equal to ND, which was the number of rational curves of degree D in P2, which we defined earlier. And this is a result proved by Michalkin in 2004, which kind of started the study of tropical geometry. It suddenly became an interesting field. And the name tropical itself comes from something done by a computer scientist. Like they defined a tropical semi-ring where the addition and the multiplication operations are replaced by multiplication and minimum operation. And so if you take that algebra and look at the hypersurfaces of polynomials, you will get these surfaces. And that the computer scientists who invented that happened to be living in Brazil, so it got the name tropical. Okay, so that is about tropical curves. Now, let me move on to the stuff I have been working on and connect this to Mehalkin's result. So that's what I'll be doing in the second half of my talk. So, so I'll start by defining a notion of how to cut a symplectic manifold. So if you have not, yeah, so I won't really deal with the definition of a symplectic manifold, just think of it as a space, you know, which looks locally like Euclidean space, and it has a certain kind of 2 form on it, again, which is not important for this talk. So anyway, so if you have a symplectic manifold, in order to cut it, you need some inputs, and the first input is a separating hypersurface. So Z is a codimension 1 hypersurface sitting inside X, and in the neighborhood of X, neighborhood of this hypersurface, you have an S1 action, which is, again, reasonably behaved with respect to the symplectic structure. And if you have such a thing, you can perform a symplectic cut. And what a symplectic cut does is it separates the manifold along this hypersurface, but then it becomes a manifold with boundary, right? So to kind of get rid of the boundary, what you do is you mod out the boundary by the S1 action, so that in the end, the result you get are actually closed manifolds. They don't have boundaries, and the Z mod S1, which sits inside both of them, is a codimension 2 submanifold, or a divisor, or a subspace, however you like to, whatever word is most comfortable for you. So, I mean, it kind of, you know, closes up. So if you, the easiest example you can think of is if you have a cylinder or a sphere, something like that, you know. So this is a sphere, and if I cut it along the middle and mod out this boundary by the S1 action, then I get 2 spheres, right? So I get rid of the boundary by modding out by S1. So that's what a symplectic cut does, and in general, this operation always produces smooth manifolds. And yeah, and both of them contain a copy of the Z mod S1. Okay, now my question is, yeah, so I'm going to ask a question which is unrelated to everything I have said so far, and this is actually the work, the stuff I have been working on, is that if we, can we relate counts of curves in the manifold X to the counts of curves in the pieces? And to start thinking of the thinking about the problem, what we do is we take the manifold X and kind of stretch the neck region, like the Z along which we were cutting the manifold, we stretch that region. And by stretching, I mean I'm changing the almost complex structure on it. So that's a slightly technical term, but for the layman, you should just think of it as just think of this picture as if you're stretching the neck region so that eventually they two come apart, the two things. But in the mathematical quantity that is changing is the almost complex structure. And then we look at curves in these neck stretched manifolds and then look at their limit as the neck length goes to infinity. Okay, and then what we see is this is what typically happens to curves. They get stretched, and some part of the curve goes into x plus, some of the part goes into x minus, and some of the stuff remains stuck in the neck, as you can see in the picture. And these kinds of maps, they are called broken maps. And they typically have a component components in x plus, x minus, and in the middle, which is the neck. So the target space of a broken map is a broken manifold, which is the pieces obtained by the symplectic cut and the neck piece. And this result is kind of a famous result by now. It's been a field of research for the last, I don't know, since 2000, so the last 20 years, is that you can show that there is a bijection so the curve counts for in the neck stretched manifold is same as the curve count in the broken manifold. So you can kind of go back and forth between them. Yeah, and this is kind of more of the same. So this is what, sequence of, if you take a sequence of maps in neck stretched manifolds, as the neck length goes to infinity, it converges to maps, broken maps, which look like those maps on the right side. Okay, so what we were looking at is what if we do this, apply multiple cuts simultaneously. And that's been, technically hard enough that there is some literature available, but mostly nobody understood it. And so, we kind of worked out everything and wrote it up, which took a long time and filled in many details which were not very well known. So that's what I was working on. And so we did so we proceed in a similar way. If there is a cut, the region surrounding it is the neck region, and you stretch it to produce many pieces. So the neck pieces are of various different forms. So those 4 corner pieces are obtained from the cut, and the ones with the blue stripes are all various kinds of neck pieces. And that's the broken manifold. And this is kind of a more abstract picture of it. The top one is a multiple cut. You stretch the neck, and you get a broken manifold, where the blue ones are the neck pieces. And when you look at limits of curves for these sequences of neck stretched manifolds, that's the picture you get. So you get the expected limit, but in addition, you get an additional piece of combinatorial data, which is the tropical graph, which looks a lot like the tropical curves we saw earlier. So we have a vertex corresponding to each of the curve components, and they are connected by lines with rational slope. So a broken map comes with an additional data of tropical graph. And one of the main technical results of our paper is that you can go back and forth in the multiple cut situation also, that there is a bijection between curves in neck stretched manifolds and curves in the broken manifold. And finally, to finish my talk, I'm on time, right? Okay, yes, so I want to relate what we saw earlier with Mihalkin's tropical curves and our broken maps. So Mihalkin's tropical curves are actually a specific occurrence of broken maps. So they are so if you take P2 and cut it in that manner, so neck stretched manifolds have this shape, and it turns out that if given a Mihalkin's tropical curve, it corresponds to a unique broken map, in the sense that you literally take the Mihalkin graph, and that is the tropical graph of our broken map. So, what happens is that you literally copy the Mihalkin graph, you take the tropical graph, and this, the maps for all those vertices are uniquely determined. So, so this is just Mihalkin, what did, it was an example of the story of broken maps and neck stretching. And I'll stop here.
Thanks a lot, Sushmita, for the really nice talk and pictorial representations of everything. Yeah. So we'll set up the next talk. Before the last talk. We will take a short break as before, just to make sure that yeah, because we're already at 3.
Yeah, you tell me whenever I'm done.
Okay, so it's my pleasure to welcome Professor Vishwajyoti Saha from IIT Delhi, and he is going to tell us about multi-zeta functions, analytic and arithmetic theory.
Sorry for the technical interruption. Sorry for my inefficiency. Thank you, and it's really a matter of pleasure for me. And 10 years back, when IMSc was celebrating IMSc 50, I was just a first-year graduate student here. So it's really a very nice homecoming. And so today I'll be talking about multiple zeta functions, analytic and its arithmetic theory. So there will be probably you will be seeing some numbers which you can perhaps relate to your field, especially let's say in physics. But I'll not be talking about those things. I'll be talking mostly mathematical theory. So let's quickly begin. I don't know. Yeah, okay. So of course, it's kind of customary for us to start with Riemann zeta function, and then it's defined on this complex half plane, right half plane, by this infinite series expression, which converges absolutely on compact subsets of this open set. So therefore, it defines a holomorphic function. Now it's not very technical, but if we just use partial summation technique, this function can be extended to the complex right plane real part of S positive, where the function looks something like this. Yeah, and this part should tell you that that has a simple pole at 1 with residue 1, and this improper integral of course converges whenever real part of S is positive. Okay, and of course that's the celebrated work of Riemann, which says that this Riemann zeta function extends to the whole complex plane as a monomorphic function with just a simple pole at 1 with residue 1, and here goes the celebrated functional equation with it. Okay, so although this particular function bears name of Riemann, it's Euler who was first studying this function, and all of us probably know about this famous Basel problem, which was about evaluating zeta of 2, that is harmonic sum 1 over n square, in terms of known constants. Okay, so we have something more general that in for any even any integer n, zeta of 2n is rational multiple of pi power 2n. So this rational number is not so important, but it's just pi power 2n that we get over here. So of course one knows now that pi is transcendental, so therefore these numbers are transcendental, and in fact they are Q linearly independent. Okay, so once we have this nice structure about the even zeta values, it's natural to inquire about the odd zeta values, and as it turns out that all these odd zeta values, it's a folklore that these are new numbers. So what do I mean by new? So if we see these even zeta values, they are just kind of pi, so effectively it's pi. But these odd zeta values are believed to be algebraically independent with these with pi, and all of them are kind of algebraically independent, so they are kind of new numbers. Okay, so now it's not clear why Euler came up with this highlighted identity, but somehow let's imagine that he was trying to multiply two zeta values, and he was trying to see what it comes out to be. So it seems like since we are in the domain of convergence, we can break our series, in whichever way we like, and we end up having these kind of nested sums, and of course this is the Riemann zeta function. So this tells something very interesting. It tells us that if we are to look for polynomial relations among zeta values, then it will perhaps be easier to read rather it as a linear relation among these numbers. Okay, and we can do some linear algebra that might be helpful. Okay, so that brings us to this setup of multiple zeta functions. I'll go through quickly. Here I need a technical open subset of C power R, and we can define this multiple zeta function as a similar nested sum over where the sum is over these indices. And it's an infinite sum, but nevertheless this will converge uniformly on compact subsets, and again it will therefore be holomorphic on this particular open subset. Okay, so once you take these new numbers, you start seeing more relations, and this one is a classic. So that goes back to Euler, which says that zeta of 3 is zeta of 2, 1. Okay, now I'm told that every talk should have a proof, so let's see a quick proof. So here I am taking one particular sum S, which is 1 upon mn and m plus n. So just AMGM inequality will tell us that this exponent of m and n in the denominator is at least 3 by 2. So therefore I can do whatever random operations or manipulations that I would like to do, and therefore if I do it carefully enough, in one hand it becomes zeta 3 plus zeta 2 1, on the other hand it's twice zeta 2 1, so therefore zeta 3 is equal to zeta 2 1. Okay, so therefore this number seems interesting, but although somehow they got lost into the literature, and they only came back due to 2 papers of Hopman and Zagier in 1992. So this subject is fairly new, around 30 years old. So let's go to the next thing. So of course I was talking about the Riemann zeta function, and I said about the analytic theory. So I will again quickly go through the analytic theory of multiple zeta functions. So we also have kind of extension. We had seen that the multiple zeta function was defined only in a subset of C power R, and one can still nevertheless extend it. But the extension is not so easy in the sense we do not have, let's say, functional equation of the Riemann type. Okay, but nevertheless it says something interesting. It says that I have certain simple polar hyperplanes which I need to explain. I will do it in a future slide, and these hyperplanes are kind of listed. So it's S1 equal to 1, like for Riemann zeta function S equal to 1, and then S1 plus S2 equal to 2, S1 plus S2 equal to 1, and so on and so forth. And this set Z less than or equal to I means set of all integers which are less than or equal to I. So there is another major difference, is that now I am going to have infinitely many hyperplanes where I might be having some problems where I can't have my function to be holomorphic. So that's the first theorem from Zhao, and I think soon after there was a theorem by Akiyama, Egami, and Tanigawa which kind of said the same thing, except that it said that okay, this list contains some of the redundant hyperplanes, so one needs to get rid of those ones. and these are the ones highlighted in red. These are the ones, if you throw them away, then you take any point on the complex plane, then this function will be holomorphic there, which are not lying in these hyperplanes. Okay. So now I have not explained many things over here, this possible, this simple, what do I mean by simple, and polar hyperplanes, what do I mean by polar hyperplanes. We are talking about functions of several complex variables, so this is more technical. So therefore, what I would rather like to do is that I would like to give you local expression of these functions. Once I give you local expressions of these functions, this will be absolutely clear what is our function, what is the part which is kind of problematic for these points, and we will see it more clearly. Okay, and as I said, of course, there is no functional equation like Riemann type. So it's of course of another interest that whether do we know how to assign values of our function, this multiple zeta function outside the domain of convergence in some way or not. So that will be quite clear once we see local expressions. Okay, so local expression means what? If I think of Riemann zeta function around 1, if I want to ask for a local expression, it will just be LoRa expansion. Now again, we are in trouble because we are doing functions of several variables. We don't have any recipe to write LoRa expansion, or there is no concept of as such LoRa expansion that way. So how do we do that? So that's the aim for the next slide. So of course, if I have a point which is in the domain of convergence, I can just write Taylor expansion. Boom, we are done. Now if we are outside the domain of convergence, what happens? That is the question. Okay, so let's try to see if we have some hints around. If we think of Taylor expansion, then the coefficients are coming from the derivatives, right? That's high school. But if I am outside the domain of convergence, how do I differentiate? What is the function? That itself I do not know. So how do we get around this? So let's go back to the Riemann zeta case, and that brings us to the paper of Stilges. So Stilges did what? Stilges did that this is of course one variable case, so I can write zeta of s as 1 upon s minus 1, that's the polar part, and we have something which is entire, and that's given by this power series, where these constants, gamma k's, these are called Stilges constants, and they are quite interesting because they are given by this particular expression. So now, here I would like to point out one thing. So let us try to see what is going on over here. So this Stilges constant is just, I am going to take this partial sum of this infinite series, which does not converge at s equal to 1, and I am subtracting some part which is going to go to infinity. So this is a kind of regularization process, and that's again fairly common in various fields, like particularly in physics. So whenever you have something infinite, you try to figure out which is the cause, like what's the cause of making it infinite, you throw that away, take the thing which is remaining. So this is exactly what we are one is trying to do here, and these gamma k's are defined in this way. And if you notice, this guy, this series is coming from taking higher derivatives of the Riemann zeta function. So therefore, what you can treat these gamma k's as, these gamma k's are rather not the derivative at 1, but rather the regularized derivative at 1. Okay, so that's how one can interpret this, and long story short, one can do a similar kind of regularization process for higher variable also. One needs to be a bit careful, as I said, there is already no standard notions of writing LoRa expansion, so one has to be a bit careful, but one can do this regularization process for this series with multiple zeta function with it. So once we do that good enough, we get explicit local behavior of our multiple zeta function around any given integer point. So let's take one example, let's take 1, 1. So what do we see? We see that zeta of S1, S2 is 1 upon S1 minus 1, S1 plus S2 minus 2, and again 1 upon S1 minus 1 times a power series, and again a power series of 2 variable. So therefore, now I understand what did I mean by local polar hyperplanes, simple polar hyperplanes. So if I take this point 1, 1, the hyperplanes that were listed there, among those hyperplanes, I have 2 of them passing through these points, on which this point is lying. So those hyperplanes are S1 equal to 1 and S1 plus S2 equal to 2. Lo and behold, if I just multiply this function by S1 minus 1 times S1 plus S2 minus 2, I get something which is holomorphic, and that's evident from this expression. So I really understand what I really mean by simple polar hyperplanes. I just need to multiply by, single factors of these equations of the polar hyperplanes, and I will get something which is holomorphic. And I can do something, I can give few more examples. Let's take the point 0, 0. Here the local expression is a bit more tricky, but nevertheless again I have some power series and some rational functions over here. So again, if I clear out the denominator, so here the only hyperplane that is interesting is S1 plus S2 equal to 0. If I multiply it out, I will get something which is holomorphic around 0, 0. Okay, that's the point. And here is one more around the point 0, 1, minus 1. So here the function is actually holomorphic. So you do not see any denominator over here. Everything is holomorphic. That's good. And that is precisely which was predicted if we go back by Akiyama, Egami, and Tanikawa, that these are the hyperplanes which you should throw away. So for instance, you should throw away S1 plus S2 equal to minus 1. So therefore, clearly, if I take this particular point 0, minus 1, it's this problem is not a problematic point. It's a fairly nice point. Okay, so I think yeah, I'm kind of in the midway. So we will go to the next half of my talk, which is the arithmetic theory. Okay, so we started doing the same thing for Riemann zeta function as well. We started looking at the values. So here also let's do that, and here the special values will be zeta a1 to ar. For the convergence condition, I just need to take this a1 to be bigger than or equal to 2, and all other ai's I take them to be positive. That's good enough. Okay, and once we take these sums, we need to have an invariant attached to them. So that's the weight, and the weight is the sum of the indices. And once we have this setup, one can define, like as I said, I would like to do linear algebra. So we can actually define certain vector spaces over Q, let's say. So the weight 0 space is just Q, weight 1 space is 0, and weight K space is space generated by all the multiple zeta values of weight K. Okay, so that's my space ZK. And again, as I said, if we, since we have have made this setup, we are going to see more and more relations. So what are few relations? Few relations are like zeta 4 equal to zeta 2, 1, 1, zeta 4 equal to zeta 2, 2 plus zeta 3, 1, zeta 4 equal to 4 times zeta 3, 1. So in fact, these are all the relations up to weight 4. This one and the previous one which I had, Euler's relation, which I had seen, I had mentioned. So therefore, what it turns out that all these relations, there is one thing common, is that unless I can break my relation into several sub-relations, I will always get relations among zeta values of which is weight preserving. On the left hand side, whatever is my weight, on the right hand side, I should be having the same weight. So that brings us to the conjecture, very first conjecture, that's due to Zagier, which says that there is no non-trivial linear relation between multiple zeta values of different weights. So that means if I consider the Q vector space of all multiple zeta values, then that has a direct sum decomposition where the decomposition is based on these weights. Okay. Now that's a very, very strong statement to make, because for instance, this particular theorem tells us that all the odd zeta values are transcendental, because if they would have satisfied a polynomial relation, then each of the segment, each of the monomial would have been of different weight, and that's not allowed. So this is very powerful. In fact, it's nothing special about odd zeta values. Any multiple zeta value would be transcendental because of this particular conjecture, and of course one should mention that this is way beyond our capacity of proving at this moment. So let's go ahead, and we can look at these spaces Zk a bit more carefully. So of course these were generated by weight K multiple zeta values. There are about 2 to the power K minus 2 of them. So these are finite dimensional vector spaces. One asks if we know what are the dimensions. So again, Zagier comes to our rescue, and he predicted certain kind of dimension for these spaces. It looks like the recurrence is kind of Fibonacci recurrence, but it's not quite, but okay, kind of similar, and we understand that these are also exponentially growing numbers. Okay, so that's the conjecture, and let's see what's the state of the art. So the first proof towards this conjecture is due to Terasoma and Delin-Goncharov, which says that okay, indeed these are finite dimensional spaces, and these decays are good enough bound in the sense they are actually upper bound. Okay, so that's nice. But do we know something on the other hand? Okay, so that's the problem that we are going to encounter. So in fact, like life is even, there is some hope in the sense that Hoffman had predicted a basis for these kind of spaces. Okay, but like I said, this is the point where we are stuck. In fact, even after having identified a possible candidate for basis, Francis Brown's work only gives us that this is a generating set. We still do not have anything about the linear independence. Okay, so that's a very hard problem. So just to tell you that how hard it is, so let's take the weight 5. So here my basis, probable basis, contains two elements, zeta of 2, 3 and zeta of 3, 2. If I want to say that they are Q linearly independent, it means to say that their ratio is an irrational number. Now any kind of statement of proving certain number is irrational or transcendental is very hard, and these ones are completely out of scope at this moment. Okay, so in fact the situation is so hopeless that the only known values of the dimension of these ZK space, these are 1s. So Z3 is 1 dimensional, Z4 is 1 dimensional. We still do not have any single known space where the dimension is at least 2. Of course, it is predicted, like 5 is predicted to have dimension for 2, but that's not known. So how do we understand these dimensions better? The way to understand them is to understand source of all possible linear relations. Once we understand that, then we might get an equality in this dimension conjecture. Okay, but again that's a conjecture by Ihara, Kaneko and Zagier. For the interest of time, I will skip that, and then I will try to just explain for the last couple of minutes an extended setup. So it's natural whenever we have a problem which we can't solve, we try to extend and see if there are elements coming from something outside which can help us solving this. So what's the extension that I'm proposing, or like we would like to study, is a similar sum, but here the indices are odd. Okay, it's exactly the same sum, indices are odd. So if I take the r equal to 1 case, you see it's just n bigger than equal to 1 to n minus 1 power minus a. And if I add the event terms and subtract, it just comes out to be some rational multiple of zeta values. Well, good. And many of you can identify that this sum is actually a Hurwitz zeta value. So that was fairly simple in case of one dimension or depth 1. But that's not so trivial in case of higher depths. It's a theorem of Murakami which says that indeed the set of multiple zeta values is lying inside the set of multiple t values, which I have taken over here. And do we have analogous predictions for multiple t values? Well, we have. We have a conjecture of Hoffman which says how these dimensions grow. This time it's exactly Fibonacci recurrence, and we know this. So therefore clearly this dimension is expected to be bigger than Zk, and in fact we have predicted basis for this thing, and all that is true. All that we have, all these predictions are there. But I would like to end with something which is interesting here. Let's look at the weight 3 space. So weight 3 space, if I write down the basis, it's T21 and T3. So therefore these two numbers, we expect them to be linearly independent, so clearly they are not equal. But these two were equal when we had multiple zeta values. When we treated zeta of 2, 1, it was equal to zeta of 3. But in this case, these two are different. So therefore, although we know how did really zeta 2, 1 became equal to zeta 3, or we know what is the source of this relation, here it seems these two are not equal. So here we are in a kind of a blind spot, in the sense, to the best of my knowledge, we do not know what are the expected source of all relations. Okay. So fine, we have extended our setup, but then we are stuck again. So is there any hope for going ahead? So indeed there is some hope. Okay. So that's my last comment over here. So there seem to exist a weight decreasing derivation on the algebra of multiple t values, which does not exist in the case of multiple zeta values. So what does it say? It says that if we just restrict onto multiple zeta values, we do not see certain maps appearing. Once we extend our setup, we see certain maps appearing. Now what it helps? It helps to distinguish T21 and T3. Why? Because T3 is effectively a zeta value, which was zeta 3 or some multiple of zeta 3. So it helps to distinguish between these two numbers. So this number upon that derivation will not vanish, but this number upon that derivation will vanish. So therefore what happens is that now I get a recipe to say that these two numbers are linearly independent, because one linear map is killing this one and not killing this one. So they can't be rational multiple of each other. So therefore that gives you that this dimension is 2. Remember, in case of the multi-zeta space, we did not even have a single space where the dimension is known to be 2. Of course, here I am not claiming that this is now settled already, but one has reduced this problem of irrationality to finding something which is algebraic. Its derivation is talking about some derivation on this algebra, so it has become an algebra problem rather than an irrationality problem, because any problem with hardcode numbers, that's much more difficult than dealing with some structure object. Okay, so that's the work in progress, getting an explicit expression of this derivation, and hopefully next time I will have something more to report on this. And thank you very much for your attention. I think I'm on time.
Little bit, you exceeded the time.
Okay.
Thanks, Vishwajyoti,
Yeah,
and
so
we have a token of appreciation for you.
Thank you. If there are any questions, I can take it outside, but yeah, we would really like to maybe move to the next stuff. Thanks.
Thanks. So there's one last talk.
One last.
Yeah. After that we can. Okay. Yes. So it's my pleasure to welcome Professor Anirban Mukhopadhyaya, my colleague from IMSc, and he's going to tell us about equidistribution. Yeah, 1 second. He's going to tell us about equidistribution, I believe. Yeah. Oh, beyond uniform distribution.
Okay, thank you. So I'm going to use the word equidistribution as well. So nothing wrong. Yes. So start by thinking about a rectangular billiard table. So this is a picture I could just download, and if you hit a ball, then it just goes to the boundary and reflects with some rule of reflection, and maybe it reflects several times before hitting a ball, or it may not hit another ball and just stops due to friction. Now let's imagine a table where you don't have friction, so it keeps moving if it doesn't hit a ball. So then some question arises that can it just keep moving, or it should hit another ball after some time? That's the question, and let's try to put it more mathematically. Will the ball come to close to every point on the table? And the answer turns out to be yes, if the starting slope is as in real line, because as of the straight line, the ball is moving in straight line, that's what I'm assuming, if the starting slope is irrational. And this is a consequence of a classical theorem by Kronecker, which is this. So if alpha is a real rational number, then if you look at these multiples of alpha, alpha 2 alpha, 3 alpha, 4 alpha, etc., and look at the fractional parts of that. So those fractional parts lie between 0 and 1, and they form a dense set. So that's the reason this is going to happen if you start with an irrational slope. Now, now we know that this is a dense set, so we would also like to know that how these points are distributed in 0, 1, whether they are equidistributed. So what's our notion of equidistribution? So our notion is that if we look at a subinterval, it should get a the correct proportion of elements. So the proportion of points belonging to a subinterval should depend only on the length of the subinterval. So if you take a bigger interval, it should get more points. If you take a smaller interval, it should get less number of points. So it should only depend on the length of the interval. And that's a definition. So I won't really call it, I'm not going to call it, you can call it equidistribution. I'm going to call it uniform distribution. So a sequence xn lying between 0 and 1 is said to be uniformly distributed if this happens. So what is this? So if you count the first n points and count the points which are in this subinterval AB, and then divide by the number of points, which is n. So that proportion should converge to the length of the subinterval as you consider more and more points. So this is what is uniform distribution. And these are examples of sequences which are uniformly distributed. So the first example is n power into alpha. Is uniformly distributed if alpha is irrational, and n power alpha is also uniformly distributed if alpha is not an integer. So you can think of n, say, square root of 2, or even in square root of n. That's uniformly distributed. In all cases we are looking at only the fractional part, because this might go up beyond 1, so you are going to look at the fractional part. And also another example with log n to the alpha. So there is a classical criteria to check if some given sequence is uniformly distributed, which is known as Weil's criteria. And this calls for an evaluation of an exponential sum of this form, and you need to check that it goes to 0. So I am not going to use much exponential sum in the rest of the talk, so I am not going to talk about this much. Okay. So let's again come back to the billiard and ask a further question. So now we know that if a ball starts from a point with an irrational slope, so after some time it's going to hit a ball wherever it is placed. So it comes close to any point actually on the table. Now the point is how much time it's going to take. Will it come to a particular point very quickly, or is it going to take a lot of time? So that's the question, that how much time it takes to come to a particular point. Let's put it more mathematically. So mathematically speaking, we are looking at the rate of convergence of this counting function. So how fast this converges to the length of the interval, which is the expected value. So this question is of course being asked for sequences which are known to be equidistributed, so that the limit, we know that the limit actually converges to b minus a, the length of the subinterval, and we now want to see how fast it happens. And this is what is called discrepancy. So this definition of discrepancy is just nothing, it's just look at the counting function and subtract the expected value, look at the difference, and then take supremum over all possible subintervals. So looking at discrepancy is an interesting problem. Of course, as I already said, that you are going to look at discrepancy for a sequence if you already know that it's equidistributed. It's a finer question. In fact, if we if you can prove discrepancy goes to 0, it is equidistributed. But you want to say how fast it goes to 0. So the first example is n alpha, the one in Kroneker's theorem. So that we already know that it's equidistributed and or uniformly distributed, and so we want to calculate the discrepancy of that sequence. So we multiply. So alpha is an irrational number. Suppose it's an irrational number, and you multiply. You take integral multiples of it and look at the fractional part, and then calculate the discrepancy. This turns out to be n to the minus 1 plus epsilon for any given epsilon with a constant depending on epsilon involved. And this happens for almost all alpha, almost all in the sense of Lebesgue measure. So for the set of alpha for which this does not happen forms a set of Lebesgue measure 0. That's what it means. And let's calculate for n square alpha. For n square alpha, it is n to the minus half. The first one is best possible, that is known to be best possible. N to the minus 1 plus epsilon is the best possible. But in very few situations, we can actually calculate best possible ones. Okay. Now, I'm going to look at some strange objects. Anup, how much time I have? I actually didn't check the watch. Oh, okay. I should go slow actually. Yeah. So, so to define what is called generalized polynomial, I need two notations. So this the first notation is given a real number. The square bracket x is the integral part of x. So that is the largest integer smaller than this number. So if you look at x on the number line, look to the left. Yeah, actually this is the left for you. So look to the left and pick the integer you hit first. So that's the integral part, and the fractional part is just the difference of that number and the least integer. So integral part can be negative, but fractional part is always going to be positive. And now we know that polynomials have two operations, addition and multiplication between numbers and the indeterminate. Now we are going to introduce these two operations into polynomials, and that's what is generalized polynomials. They are going to look like this. So these are examples. So there are many variations possible. So I just read out the first one. So first one is the 3x, so that's just a standard monomial as usual monomial. But the second one has this bracket operation. So we are looking at x square, multiplying it by square root of 2, and then look at the integral part, not the entire thing, but the integral part of it, plus a constant. That I am just writing pi to be dramatic, but it just can be any constant. And also the fractional part operation. For example, the third generalized polynomial has a fractional part operation. And also nestings are also possible. The second example has a nesting. So it has a nest of these square brackets. So you are looking at the integral part of 5x, multiplying it by another number, adding something, and then again looking at the integral part, and this kind of nesting is possible. So these very strange objects appear in many places, and many of them are known to be uniformly distributed. They generate uniformly distributed sequences. So there were lots of dynamical study on this. So my point is not going to go into those things, but what I work on is to calculate generalize the discrepancy for these generalized polynomials. So I look at very simple generalized polynomials because things are known for that only, and even there it's a bit complicated. So I am going to look at a very simple generalized polynomial, no nesting or just one bracket actually. So Px is a usual polynomial of degree d with rational coefficients, and then we consider this sequence where I take two real numbers alpha and beta, So look at this Pn, where P evaluated at positive integral values multiplied by alpha, then the integral part, and then multiply by beta. So that may be of course bigger than 1. So you would look at the fractional part then. So every time we are looking at the fractional part so that it lies between 0 and 1 whenever we are talking about this uniform distribution. So it's known that this is uniformly distributed if 1 alpha, alpha beta, these 3 real numbers are linearly independent over rationals. So that's known. So that's the situation where it is uniformly distributed. So we can ask what the discrepancy is. And discrepancy, so we are going to, so that's a rate of decay. So we would like to find an upper bound, as I have already shown you examples that we would like to find an upper bound, then we know how fast it decays. It may not be best possible, but we want to find some upper bound which goes to 0 as n goes to infinity. So this is a result with Olivier Ramare and Kashi Vishwanathan some years back, where we could prove that for almost all reals, the discrepancy of this polynomial. So this n has a very strange looking exponent. So I am not going to read it, but better look at an example. So when the degree is 2, this turns out to be n to the minus 1 over 15. So that's a negative exponent. Of course, you would have to get a negative exponent. A positive exponent is meaningless. So that's the kind of thing can be done. This is not a best possible result. So lot of improvement is expected. And this depends on what I am calling irrationality type. I am not explaining. So it depends on how irrational this pair is. So, but in the end, for almost all, you can prove this result. It actually depends on the irrationalities. Okay. So we also looked at this same question for primes, where you don't look at all integer multiples, but only prime multiples. So P runs over primes. So you can ask that question. So here we are not looking at higher degree polynomial, just linear polynomial. So n alpha, and then take integral part, multiply by beta, discrepancy of that. The result is of course worse than what we get there, because it's difficult to handle primes. So I would actually go to a further question, probably a more subtle question. So more subtle question. Oh, that's fine. I probably need 2 minutes. So yeah, so more subtle question. So I'm looking at this real number sitting between 0 and 1. Now what I want to ask, that how their gaps are distributed. Again, in this case, we are again looking at sequences which are already uniformly distributed. So they are already very nice. So now we are going to look at their gaps, and we want to know how the gaps are distributed, how close they are. And that calls for a definition. So this is what is called a pair correlation statistics. There are many pair correlation statistics at many places. This is for this sequence, this particular situation. So let me explain what it is. So I am looking at pairs xn, xm, and then looking at the difference. But they are numbers between 0 and 1. So the difference might exceed that interval. It might become negative. So we won't do that. So we would look at the nearest integer distance. So if I do that, then I am counting the pairs whose distance is less than equal to s by n, and then multiplying that number by 1 over n. So that's like a normalization, so that we expect this this quantity to go to 2s when n goes to infinity. So if that happens, then we say that the sequence has Poissonian pair correlation. It's actually the gaps are distributed as Poissonians, so that's what is playing behind it. So then we, if this happens, then we would say that this is this has the sequence has Poissonian pair correlation, or PPC to abbreviate it. And all sequences which has PPC are uniformly distributed. It's much finer. And very few examples are known actually. Explicit examples are very few. For example, this sequence n alpha, which is uniformly distributed for every irrational alpha, is never PPC for any alpha. That's known. And the sequence n square alpha is supposed to have PPC for almost every alpha under very mild conditions on alpha, but even in that case, very small, very few examples are examples have been actually proved. A nice exception is the sequence square root of n. So we are looking at the square root of n, then of course the fractional part. So that has PPC. So PPCs are difficult to prove. So it's so it's interesting to look at what is called metric results. So we are trying to look at from an almost all perspective. So let's just a simple definition. So a sequence of positive integers. Let's look at an increasing sequence of positive integers. An. And we say that that sequence has metric Poissonian pair correlation, or MPPC, if An into alpha has PPC for almost all alpha, almost all real alpha. And in a joint work with Tanmay Bera and Mithun Das, so my student and a Mithun was a postdoc in IMSc, so it's an IMSc work as such. So we looked at this question in higher dimension and proved, so this is just a corollary of what we could prove, but it is just easier to state. So let me just explain. So I'm looking at two-dimensional sequences. So the first component is fractional part of n alpha, and second component is fractional part of n square beta. Alpha, beta are real numbers. And then we could show that this has Poissonian pair correlation for almost all alpha and beta. So the subtler thing is that when you are in higher dimension, you have various choices of distances. So various choices of norms. So we could prove this in both in 2-norm and infinity norm. Of course, there are infinitely many norms, so and they require a different kind of treatment. And there is another example, it's a little more complicated. The first example is more interesting because the n alpha, the first component sequence, does not have PPC, but when you club it with a sequence which has PPC, it is having PPC. So that's the kind of example we could construct. So I'll stop with that. Thank you for your attention.
So thank you, Anirban, for the nice talk. So now I'm going to, please stay, don't go right away. I'm going to hand over, so this is the end of academic talks for this session, but we do have a book release. So I'm going to hand the mic over to Professor Ravindan, who will, yeah.
So this is, continuation of what we have been doing. part of the celebration, it is my honor to arrange a book release function, a very short book release function. The person who has written this book is our former professor, Professor K. Srinivas Rao. I think most of you know him very well. He is, in my opinion, is an encyclopedia of the life and works of Ramanujan, and he had sort of popularized the works of Ramanujan in many ways, working on certain number theory problems and also writing a lot of articles about Ramanujan and reaching out to people. So it is an opportunity to actually introduce him also to those who have not seen him. And also, I request Professor Balasubramaniam, our former director, to come onto the stage and really, take the book actually. So release the book rather. Should I release or he should release actually? Yeah. No, I'll give it to you. Whichever is. So I'll give it to him. That is the procedure. And this is the Tamil version. So, it's okay. I think you can listen to me.
Okay. Can I say a few words? Can I say a few words? Yeah. The book was published in the year 2012. That was the English version part of it. And the Tamil translation is an idea which came mainly because there were people who were saying that it will be good if it is written in Tamil. So this book was translated with the help of a gentleman by name Dr. Srinivasan, who is a member secretary of the Tamil Nadu State Council for Higher Education. Due to his preoccupations, he is not present here. I want to give 2 copies of this book to the library of the Institute, and of course, I will give a copy to the director of the Institute for his personal use. So as I said, this is the cover of this book, and the cover of the other book, which was shown, is the English version, which has the statue of Ramanujan, which was made. For those of you who are interested, I was able to, thanks to Dr. R. Chidambaram, in the Ramanujan IT City, when they asked for a bust of Ramanujan, I was able to get a full-length statue of Ramanujan made and installed. Of course, it is not available it's not in the public places, but those who are interested, I would be happy to take you and show you. It is in the Society for Electronic Transactions and Security, where Dr. Balasubramaniam was the director for some time. So thank you very much for giving me this opportunity. So I hand over the copies of the book to you, sir. Thank you very much.
Since we are running late, let's resume around 5:20. Oh, maybe 5:15. 5:15 we'll resume our.
Hello, welcome everyone to the last but the most interesting session of IMSc 60. And this session highlights all the contributions from our institute members to the audience. So I think you will be interested in knowing what we are doing here in our institute. And the first talk of the session is by my colleague, Professor Jaya Ayer, and she will tell us about topological invariance arising in geometry. Jaya, please.
Sure. So, yeah, firstly, I thank all the organizers for organizing this wonderful meeting, and I am also glad that many of you are still around for this last session, though I guess it's been a tiring session for everybody. So, thanks to all. So, actually, in this 20 minutes, I just want to give a flavor of some topological invariants which occur in geometry. In fact, actually in the title it was algebraic geometry, but I realized it is more differential geometry. So let us call it geometry. So what do I mean by topological invariants? Okay, so just to give some idea actually what I want to discuss. So, since this talk comes towards the end, so I suppose all of you know what is a topology. So I'll just say one or two sentences on it, and mainly I want to focus on finite cell complexes and their invariants. So these invariants lie in the cohomology groups or the homology groups. So these cohomology groups or the homology groups are certain finitely generated abelian groups which one associates to any topological space. So in particular we would focus on the so called manifolds, so which are supposed to be good topological spaces. So these are the items I want to first discuss or at least mention. And then the earliest invariant is the Euler characteristic class. So this is actually a number which you can associate to good topological spaces. And so then the next question is that, so as I said, you start with a good topological space and you associate certain cohomology groups, so which are some finitely generated abelian groups. So how do you recover the classes? So these invariants, so actually even the cohomology group you can think of as an invariant, it's a finitely generated abelian group in each degree. So these groups in fact recognize the cell structure of your topological space. Okay, so that's what I want to discuss. And how do you recognize the classes in these cohomology groups? So for that reason one introduces vector bundles, so which are certain structures over the manifold. Okay, so you can think of them as locally trivial. So something like your manifold times your some Rn, your Euclidean space n dimensional. And then for such vector bundles you associate certain invariants which are certain elements in the cohomology groups. So the question is that is every element of your cohomology group recognized as an invariant of manifold, of the manifold, okay, for some locally product structures. So that's something we don't know. So at least in even degrees this is true, at least with rational coefficients, but in general for the odd degree cohomologies we don't have much idea. And so at least in this talk I want to first discuss Chern-Simons theory, so which says that at least if you look at locally flat structure over some manifold, you can associate secondary classes, so which you can think of as invariants, cohomology classes in odd degree cohomology. And but we don't really know that if these classes are actually cover your whole odd degree cohomology groups. But at least what we can do is that, is there some other way you can associate invariants? Because if you are looking at some manifold, for example a topological space which underlies a topological space, and so how do you recognize the skeletons, that means in each dimension of your manifold? So what are the invariants you can associate? And so for that actually you are not just looking at a locally product structure on a manifold, but you also want to look at a path of such structures, or you can take a loop of such structures and so on. or higher dimensional simplices of such structures, and you would associate certain cohomological invariants. So these are the cohomological invariants of moduli space of flat connections. And I would end with certain questions on the rationality of such structures. Why isn't it? Excuse me. Actually, it's not moving up and down. This one is better. This one. Okay, left and right. Okay, thanks. So, sorry for this. So let me just start with what is a topology. So at least for this talk, I'm not going to go for any concrete definitions as such, but I just want to say that you start with any space, maybe in R2, R3 and so on, and then you identify it with any other class by saying that, okay, it's going to be the same if stretching, bending, but not tearing, so these properties are preserved. So for such a space, we want to associate cohomology groups or homology groups, and say that we want to recognize such spaces up to such equivalence classes, and so which we call as homeomorphism up to homeomorphism. And so for that reason, so we associate all these groups like the fundamental group and so on, homotopic groups and so on. So the simplest spaces that we know are the real line, the two-dimensional real plane, the three-dimensional real space, and more generally you can look at the n-dimensional real space. So these are the so-called Euclidean spaces. And now actually you can also look at non-Euclidean topological spaces. So these are going to be the, for example, your circle, the first examples that we come across. So these are the circle, donut, torus, sphere and so on. So now what are the building blocks of good topological spaces? So if we just start with some arbitrary topological space, so this is just some subset in some Rn and so on, with some induced topology from your ambient space. So if you look at such spaces, so then you want to understand them, but it is going to be very complicated if you are just restricting to a very general setup. So we actually restrict our attention to some spaces which are somewhat tractable, and so those we call as good topological spaces. So at least up to stretching, bending and so on, they have to look something which is recognizable, which we can try to understand and do some geometry and so on. So what would be the good building blocks actually? So in dimension 0, it is just a point, and in dimension 1, it is the unit interval, and in dimension 2, you are going to take the unit disk, and dimension 3, it's the unit sphere. So these we call as the unit, as the open cells in each dimension. Okay, so a finite cell complex, so it looks like a finite disjoint union of such open cells in varying dimension. So for example, if you take a circle, so it is a finite union of an open interval and a point. So this is actually up to stretching and bending and so on. And so where if you take a circle, you remove a point, so then actually what you get is an open interval. So it is a disjoint union of a one-dimensional open cell and with a zero-dimensional cell, one zero-dimensional cell. So similarly a sphere, so it is a disjoint union of a two-dimensional open cell and a zero-dimensional cell, which is a point. And then one can check further that even your torus or even actually if you take higher analog of torus, that means some compact Riemann sphere with several holes. So these can be written as disjoint union of two-dimensional cells, one-dimensional cells and so on. So these are some nice finite cell complexes that we first come across. And so now actually what is the invariant you can attach to such topological spaces. So this is the dimension, this is the coarse invariant you can first attach. Coarse because actually you are just going to look at the largest dimensional constituent cell of the space, and so this you can call as an invariant. So at least you would know that if two spaces, so they have different dimensions, so they are not going to be classified as one class. So at least that gives some kind of a handle on how to look at finite cell complexes and when you want to classify such spaces. So the first invariant you can classical invariant which was attached. So this is the Euler characteristic class. So for a finite cell complex, so you start with a finite cell complex. So this consists of vertices, edges, faces and higher dimensional pieces. And now you just look at the number of such vertices, call it V, E and F, and more generally take alpha k. And so you can define the Euler characteristic to be the alternating sum of all these numbers. So this would be the Euler characteristic class. So this is a number. So for example, if you are going to look at a circle, so as we said that it consists of a one cell and a zero and one zero cell. So the Euler characteristic class is going to be 0. So similarly you can check for a sphere and torus and so on. Now actually if you are not just looking at finite cell complex, but our topological space has additional structures, like for example it comes with some manifold structure. So why manifolds are important is that when you are studying spaces, we just don't want to look at its topological, like what are the invariants and so on, but we also want to do geometry. And so geometry can be done if we know how to differentiate functions, how to integrate functions and so on. So for that reason, actually I think the classical mathematicians long time back, so defined manifolds, so which are going to locally look like open balls in Euclidean spaces. So because in Euclidean spaces we can do calculus, and so this calculus then you can transport to manifolds. So now actually we have this topological invariant which is the Euler characteristic class. So it was observed by Whitney that this topological invariant can also be recognized by defining certain Stiefel-Whitney classes, so which are certain cohomology classes in the cohomology groups of your underlying manifold with Z-mod 2 coefficients. So it's actually a bunch of invariants, it's not just one invariant, so in different degrees. And now actually if you take the top Stiefel-Whitney class and then you integrate it over your manifold, you recover your topological invariant, the Euler characteristic class. So the Euler characteristic class, which is actually topological data, so this is also determined by the smooth structure of your manifold. So actually Whitney explored this idea further, and he said, okay, what is great about looking at vector fields? You can also associate cohomology classes for other locally trivial, locally product structures over your manifolds, so which we would call as the vector bundles. So basically what we have is that suppose you have a locally product structure over a manifold which we call as a vector bundle. So corresponding to that we associate the primary classes or the primary invariants, so which we call as the Chern classes. So what we need to remember is that these Chern classes are certain cohomology classes in the cohomology groups of your manifold. So this is actually a bunch of classes according to the rank of your vector bundle. And now what is connection? So this is some coarse invariants you can associate to such locally product structures. So but actually as we have plenty of physicists here, so I hope, and so we can also look at the additional structures on such locally product structures. So these are called as the connections. So connections is some kind of a formula to differentiate vector valued functions on M, because as I said that you have a locally product structures, so that one fiber is a Euclidean space. So you can look at the vector valued functions and then you want to know how to differentiate them on manifolds, because remember that our space is no longer a Euclidean space. So we have to define some formula how to about differentiating them. So these are called as connections. So now associated to such a connection, you can by Chern-Weil theory associate invariants. So these are certain cohomology classes in the odd degree cohomology of your manifold. A priori, because these connections are on some vector bundle, so you forget the connection. So corresponding to a vector bundle, you can associate Chern classes in the even degree cohomology groups. And now if you associate connection, so you can do better. You can do better and you can define cohomology classes in the odd degree cohomology groups, and so these are called as the Chern-Simons classes. So what we need to remember is that you can define for this connection a vector bundle associated with a connection which we can assume to be flat to begin with. So flatness essentially means that because when you have a locally product structure, so when you move from one chart to another, the transition maps, so they are essentially constant maps. So that's what we mean by a locally flat connection. And so you can associate classes in the odd degree cohomology groups. So now actually, so this gives some idea about how the cohomology groups look like actually, because you are associating invariants. So actually the first question we can ask is that, so suppose you start with the manifold, and then what we are doing is that you look at certain structures over your manifold, the classical one, say coming from Whitney and so on. So where you associate certain cohomology classes coming from product structures, locally product structures. And so the thing is that, do all these invariants generate your cohomology groups actually? And in fact, actually, if you are just going to look at the even degree cohomology group, so it's a theorem that it's a classical fact that in fact at least with Q coefficients, any such cohomology class can be written as expressed in terms of the Chern classes of vector bundles. Chern classes, remember that, so these are the primary invariants of a vector bundle. And now actually if you associate additional structures to your vector bundle, so what we are getting are some classes in the odd degree cohomology classes, cohomology groups. And so we can ask that, I mean, are these invariants good enough actually to cover your cohomology groups? Because why we are interested is that because the cohomology groups, so these encode the topological data of your manifold. So are these good enough actually? So for that actually, as I said that associated to a single vector bundle and a single flat connection, you can associate classes. And now actually the question is that, okay, now suppose you have a path of flat connections. So can you associate a cohomology class? So in fact it is true, we can do that. And so actually this is via another cohomology theory called the differential cohomology theory. But in any case you can associate certain classes, and these classes are independent of the path of the connections you choose. Yeah, 5 minutes, yeah, I think it should be done. So more generally, what we can do here is the following. So in fact you look at the simplicial set formed by sequences of flat connections under the gauge group transformations. And so what we mean by this terminology is that you can just look at so in each degree, so remember that you have a manifold, and now we want to associate another manifold, so which or a topological space which underlies a simplicial set. So simplicial set, I mean that for each integer, positive integer, you associate a free abelian group determined by some set of formed by sequences of flat connections. Okay, so this is what we have, and so essentially for example, if I take a path of flat connections, so that you can say it's a one simplex because I have the two endpoints, the vertices and an edge joining them, and so for each point it parameterizes a flat connection. So that's a one simplex. And now if I take a triangle, for instance, a filled triangle, so for each point on that filled triangle, so I would associate a flat connection and so on. So you can look at higher dimensional analog of that in each degree, and you can form a simplicial set so that it recognizes certain maps and so on. And then what we have is that that there exists homomorphisms from the homology groups of such a simplicial set to the cohomology groups of the underlying manifold we began with. So essentially the last sentence says that you look at the moduli space of flat connections on a manifold, and so what we can do here is that you can actually in fact associate homomorphisms rho k, and which takes values in the cohomology groups of the manifold with coefficients in C mod Z. So this is some extension of the classical Chern-Simons Cheeger construction, and because where which can be thought of as right. The classical Chern-Simons construction you can think of as map on the pi 0 of your moduli space of flat connections. Just on the connected pieces of components of your moduli space of flat connections you get some maps, and so that construction you can extend further by associating invariants to such simplices and so on, and so you get well defined homomorphism. So the question which I want to ask is that what is the nature of this homomorphism? I mean both sides they are groups, and both sides they are finitely generated abelian groups, and so what about these maps actually, like is it injective, surjective and so on. So surjectivity is something we would appreciate, but it so happens that we have the classical Chern-Simons question which says that even at degree 0 level, so I think the expectation is that the invariants take values in Q mod Z coefficients, so that means they are torsion. So I think the question we could just extend for the higher order maps as well, and ask if they lie in the torsion subgroup of such cohomology spaces. So I think these are some questions, and yeah, if you have any interest actually further, you can drop by. Yeah, thanks. Yeah. Thanks.
Next speaker is Devabrata Adak. Devabrata will tell us about the first 10 to the power minus 32 seconds after the universe.
Thanks for giving me opportunity to speak in this special occasion. So today I'll be talking about the cosmic inflation. Yeah, so today I'll be talking about the cosmic inflation, which possibly happened right after the Big Bang. And in the opening slide, I am showing you the logo of CMB Bharat Consortium along with the satellite image they have proposed to ISRO. We'll get to know about this in details at the end of my talk. Let me begin with the school day stories that we have been told that our universe is described by the standard Big Bang model. What this theory is about? So this theory tells that our universe began and at around 14 billion years ago, when the universe was like a hot soup of the particle and the radiation, and this starts to evolve and expanding according to the this Friedman-Robertson-Walker metric followed by the Einstein GR. And the quantum fluctuations right here just after the beginning of the universe have grown to form the present day structures of the stars and large scale structure around us due to gravitational instability. However, this model never tells you what causes this expansion. And it never also tells you where does this matter and radiations come from. This model assumes that your space is somehow filled by this matter and radiation, and suddenly for some unknown reason we have access to it, and it starts expanding according to this space-time geometry. This Big Bang model is actually a bangless model. It's just an aftermath of the bang of the Big Bang. So to fill this gap, we need some prequel. During the early 80s, people have started to think what is the possible theory of that, and Professor Alan Guth come up with this idea, the inflation theory. So what this theory is about? This theory says that the inflation proposes a repulsive gravity material. So this is counterintuitive than our notion of the Newtonian gravity. But believe me, under some circumstances, the Einstein GR can give you the repulsive gravity. So this repulsive gravity material stretches your universe so rapidly, exponentially, and within very short duration of time, this 10 to the power minus 35 second, it expands our universe at least 10 to the power minus 29. It can be more, but just to be consistent with the data, we at least need to have this 100 doublings of our universe. It should stretch at that, but by that amount. So, but this repulsive gravity material is very like unstable, and that's why this inflation phase doesn't stay very longer period of time, and quickly decays, and this decaying energy produces the primordial particle soup, and that's why this inflation ends, this prequel ends, and our standard Big Bang model starts. So as an observer, my concern is not to judge which model of the inflation is doing better or which is doing worse, because there is no single solution. There are at least hundreds of thousands models which can give you the exactly same solution. My concern is, if the inflation is the correct theory, I should see some signature in the cosmic microwave background polarization. What is it? So the very common thing of this inflation model is, so it can predict this gravitational wave. So it stretches and contracts the space and creates this tensor fluctuations, and when it passes through the hot plasma, so it creates this nice quadruple pattern around the scattering electron at the last scattering surface. The last scattering surface is the time when the CMB photon decouples from the matter, and it had happened around the 400,000 years later of the Big Bang, and in terms of redshift it is 1100. So when this gravitational wave passes, so this quadruple pattern creates around the scattering electron, and it generates this Cardley polarization pattern. We call this the primordial B mode polarization. So there is another types of the polarization which called the E mode polarization, but that is not the sourced by gravitational wave. So that is sourced by the scalar fluctuations generated during the inflation. We know the amplitude of this mode, but we do not know the amplitude of this mode, because we do not know at which energy scale this inflation had happened. So that's why we parameterize it in terms of the tensor to scalar ratio, which is related to the inflation energy. So if the inflation had happened, I should see this Cardley B mode polarization in the CMB. In the last 3 decades, we had a fantastic journey using these 3 space satellite missions from very coarse resolution to the very high resolution CMB map, and along with some ground-based CMB observations. And so where we stand, this is the CMB temperature fluctuations power spectrum. So this power spectrum actually tells if your 2 points along the sky is like separated by this angle, how these CMB photons are correlated. So this data point matches with the lambda CDM predictions very well. And also we have some observations on the E mode polarization. However, we do not have any observation, or there is no predictions at which energy scale this inflation had happened. This is the primordial B mode power spectrum, but but generated from the simulation, not from the data. So as of now, we have only the upper limit of the tensor to scalar ratio of 0.036, so this B mode power can have any tensor to scalar ratio below this. We do not know what this is exactly. So far, the CMB mission was dedicated mainly to the CMB temperature anisotropy measurement, but in the coming decades, we are going to observe the CMB polarization, and all of the CMB mission will be dedicated to the CMB polarization measurement. So here is some upcoming CMB mission from the ground. So this is the CMB stage 4 mission, which is under construction in the South Pole, and this is the Simons Observatory, which is also under construction in the Atacama Desert in Chile. Hopefully, these two observatories will be functional at the end of this year. So we have also the space mission. So this is the Lightbird space mission selected by the Japanese space mission, the JAXA, and it will fly to the Earth Sun second Lagrangian point and will observe the CMB sky with very low resolution. So the major target is to detect only the inflation, but it doesn't have the very broad science goal. But we can achieve the broad science goal using some missions like the PICO, which is in the NASA's concept phase study. So this has not been proposed yet, but this will scan the CMB sky with very high resolutions and mainly on the polarization detections of the CMB. Now let me discuss what we Indians are doing in this worldwide effort. So this is the CMB Bharat Consortium. So they have proposed this ECO, the Exploring Cosmic History and Origin. The mission name is ECO, but popularly this is known as the CMB Bharat mission. So this mission was inspired by the European Space Agency's core mission, so when that was proposed at 2017, that this mission's budget did not fit with ESA's M+ envelope. So that's why the ESA encouraged European Cosmology Consortium to consider a major international collaboration, and at 2018 the Indian Cosmology Consortium took this advantage and proposed this ECO mission with some modified version of this core proposals to the ISRO. So this is on 2018 this had happened, and this was like in the first phase selection process, but we do not have the fund sanctioned yet. So this mission will have this 20 frequency band starting from this very low gigahertz to the very terahertz range. And so you can see, so this dotted line at the noise curve for the Planck, for this Lightbird, and for this the ECO mission. So you can see this 20 frequency channels are designed in such a way that it can drop the noise by orders of magnitude compared to the Planck noise. However, the noise is not only the problem. The problem is something else. This is the CMB sky looks like when we tune the CMB satellite when we scan the sky in the CMB frequencies. So you can see, so there is a CMB photons, but this is highly obscured by some other emissions. And this is in the low frequency, that is barely you can see the CMB, but at high frequency you cannot see the CMB. So because at the microwave band, the CMB is not only the component. So we have the similar emission from our own galaxies as well. At the low frequencies, this is dominated by the synchrotron from our galaxy, and in the high frequency, this is dominated by the dust emission. So that's why you cannot see the clear CMB sky. So similarly, this is for the polarization. So these are the map from the Planck at these 7 frequency channels. So you can see this foreground emission drops like till 100 gigahertz, then again increase, because the foreground emission drops like till 100 gigahertz, and again it increases. So if you compare the relative amplitude, the relative B mode power across the frequencies for these three components, the dust, synchrotron, and the CMB. So this is the signal we are going to measure. So this is the tensor to scalar ratio for which the CMB signal we are going to measure. Since CMB is the constant across the frequency, that is why this is the horizontal line. And you can see that the signal is order of magnitude obscured by the dust and synchrotron. At the low frequency, the synchrotron dominates. At the high frequency, this dust dominates. Then my job is to develop the very efficient cleaning algorithm to disentangle this foreground emission from the CMB. How many minutes? Okay, so let's skip this slide because I wanted to give you some flavor what we actually do. But we have very efficient foreground cleaning algorithm. So these are the 4 cleaning algorithm which Planck collaboration had used to disentangle the CMB from the foreground. So let's not get into details about the individual algorithm. Rather, I would show you some forecast study on the CMB Bharat instrument design. So here we have used the 2 very famous cleaning algorithm called Commander and the needlet internal linear combination method, and we have used the various foreground model and passed the frequency maps to these algorithms to clean the CMB from the foreground. Then we study how much the residual foreground can bias your tensor to scalar ratio estimation. So you can see the most of the foreground model can give you the null detection because my input tensor to scalar ratio was 0. However, we could not clean this foreground, the synchrotron foreground, because we do not have the many frequency channel at the low end of the spectrum. That's why when the synchrotron model becomes complicated, we cannot clean this properly. So that's where I will end. So summary of my talk is the primordial B mode is a promising probe of the cosmic inflation. However, the main problem is the foreground, which is at least 3 to 4 orders of magnitude higher than the signal we are going to target, and the B mode with very high sensitive space missions or the very high resolution ground based mission. I think we have the enough robust cleaning algorithm to disentangle the CMB, and hope we can detect the inflation in this decade. Thank you.
I'll put it in my pocket.
Can start. Hi. This talk will be based on this particular work with Subhashish Banerjee and Dr. C.M. Chandrasekhar. Let's start. So I would like to start with a good old classical random walk, where of a coin. So the coin, or somebody rotates a coin, or a coin rotates, and you get either a head or a tail, and depending on the result, the coin is moved either to the left or the right on one-dimensional lattice, right? So these are the 2 operations, the toss and the movement, and we can try to calculate what the probability distribution is after some time. And this is the graph I made in my first sem StatMech class, and you can see that the variance of this of such a walk increases linearly with time, right? But what happens when you give the coin the freedom to be in 2 particular states at the same time? Now let's call the tails the 0 state, and the heads will be the 1 state, and now it is in a superposition. And now you put your decision making operation on the superposition, and what you will essentially do is you will spread the particle over a lattice in a superposition, right? And so at the end of this, so you see that you get a particle or a state which is spread out on the lattice, and it also has a degree of freedom, which is we'll call it the spin or the coin degree of freedom. So it resides in a Hilbert space of a position and a coin space, right? Now, what happens in a quantum walk is that you have replaced the toss with a SU2 rotation. It need not be an SU2 rotation. If you have higher degree of freedom, you will have SUN rotation. And conditional shift is, can be written down as an operation like this. And this is just one of the example of a shift. Like this shift operation says that if the state is in 0 state, you go one step back. If it is in 1, you go one step forward. But you can have almost infinite number of such shift operations. And this shift operation is the one which is somehow entangling or in some sense interacting agent between the 2 degrees of freedoms, right? And the walk operation as a whole is consecutive action of a coin and a shift operation, right? And you can do this walk multiple times on a state, and then you calculate the probability of finding the particle. You sum it over all its spin degrees of freedom. I'm calling it spin, the coin degree of freedom, and you can calculate what the probability distribution for this particle is going to be. And it turns out that the variance actually increases by as t square. And it's here where this property of this ballistic propagation property of these quantum walks is very useful. And we use it just like a random walk is used in simulations and in algorithms and in many, many areas of physics. Quantum walks are being used similarly. There are algorithms which are quadratically faster, for example, search algorithms, which can be simulated using a quantum walk. And at the same time, quantum simulations is a huge branch of quantum simulations is a branch of quantum information which is blowing up. And it's because of the ease of performing quantum walks and the varied amount of systems that it can simulate just by changing the parameters of the quantum walk. As I showed you, there are SU2 parameters that you can tinkle with, and then you can also change the way the shift operator tells you to move backward and forward. And you can change the dimensions also. So in that sense, quantum walks and how it can be easily performed in a lab. The kind of quantum walk that I am talking about is you can have an electron with 2 degrees of freedom if you can somehow trap it, or you can use a photon if you can keep the coherence for long enough time, right? So you can perform these quantum walks in a lab easily, comparatively. Now, important aspect of these quantum walks when you're doing them in the lab is that you have to think about the effect of the noise, right? And what we know so far about the noise and how to model it comes from these particular 2 equations. The first equation is the stochastic evolution of a quantum state. It was developed in 1960s and 70s. And the second is the dynamical equation, which tells you at one particular time how the system evolves. I have highlighted the S in both the equations just to show that the S stands in both the equations stands for Sudarshan, and this being the IMSc's event, just to highlight that it has these 2 equations which form the cornerstone of our understanding of open quantum systems have a strong IMSc connections. Now, but that was not the full picture. Non-Markovianity is the kind of noise. Sorry, I think I forgot to mention that the second equation comes when you have Markovian assumptions, especially, and those assumptions are especially strong when you have, or they're valid when you can have weak system environment interactions. But that is not always the case. And evolution at a particular time can depend on the history of the state at some earlier time, right? And one mechanism for this is what this diagram is trying to show is that if the interactions are strong enough, the history of the interaction between the system and the environment can affect the environment at a later time. In some sense, it is the idea of information backflow, right? And this is one of the ways non-Markovian effects can creep in. And now we will look into a particular kind of a particular way of modeling this noise, which is the non-Hermitian evolution, but in particular the PT-symmetric non-Hermitian evolution. Now in quantum mechanics, for closed system at least, we want our operators to be Hermitian, because hermiticity ensures that the results of the observations are real, right? So you can define them as operators, but the converse is not true. There do exist non-Hermitian operators which have real eigenvalues, and they are exactly these operators which are invariant under the subsequent action of parity and time reversal symmetry, parity and time reversal operation. So these are PT-symmetric operations, PT-symmetric operators. So PT-symmetric Hamiltonians, for example, will have real eigenvalues even if it is not Hermitian, right? So where do we see PT symmetry in nature? One of the most well-known areas are when in optical systems, when we have equal gain and loss of amplitudes. There we see PT symmetric, those systems can be described through PT symmetric Hamiltonians, right? And I like to see it as some sort of coarse graining, because if you're losing and if your source and sink are equal, through some coarse graining, you can kind of go back and assume that there's nothing much has happened. No, there is no loss and no gain. But yeah, there's a more rigorous way to put it, which we won't do here. Now, there's an idea of pseudo-hermiticity where all PT symmetric Hamiltonians satisfy this particular equation. So all the operators that satisfy this equation are called pseudo-Hermitian for some Hermitian matrix or Hermitian operator eta. And it was shown that if you redefine your Hilbert space by redefining your inner product in your Hilbert space, inner product between two states in this particular way, where you put eta in between the two states, through this redefinition, you write down your Schrodinger equation or von Neumann equation. You get back the original equation, where even if this H right now is non-Hermitian, you get this equation which is true only for Hermitian case, as we saw in the previous slide, right? So in some sense, for PT symmetric Hamiltonians, one can establish an equivalence between unitary and non-unitary dynamics, PT symmetric non-unitary dynamics. And now the idea is to extend it beyond PT symmetry. And can we even do it, right? Can we find the slide shows that the inner product that we defined was, the inner product that we defined can be written down as the inner product between, can be written down as inner product between this dual vector, which is redefined using the matrix eta, right? And that's why it is called a metric, although as to make it sound like this is like a space-time metric, but as far as I know, the analogy ends here, right? But it is but this metric can be found for a given particular H, even if it is non-Hermitian, and it was shown in 2019, right? So what do we do once we have a metric like this? So what we wanted to do is, our system, as we initially talked about, consists of a position degree of freedom and a coin degree of freedom, right? And we are concerned in scenarios where the walk completely as a whole is interacting with the environment. And we want to find out how the coin and position interaction is changing with due to this noise that the whole walk as a whole is experiencing. So we are interested in and because the coin space is small, we can study using numerical techniques easily. So we want to look at how the coin dynamics is changing because of the non-hermiticity of the walk as a whole, right? So we redefine, so what we do, what we have done in our work is, one of the work is to construct this reduced dynamics using the metric formalism properly, which in our knowledge has not been done. and we contrast it to the another usual way of defining a state, a reduced state, where we divide or redefine at each time. We redefine it by dividing it by the trace of your density matrix, because remember, the unitary non-unitary evolution will not preserve the trace, right? So at each point you will want to divided by the trace. While in the first scenario, where we are using the metric formalism, you don't have to do that, right? So the first one is a linear operation, and the second one is nonlinear. And this difference is important because, so there are the last two slides of my talk now. I'll just show you two graphs. First one is showing you the non-Markovianity of the reduced dynamics. As I said, the reduced coin dynamics will be non-Markovian because the interaction is strong. But how is that non-Markovianity changing when you are introducing non-hermeticity in the walk as a whole, right? For that, we redefine non-Markovianity in this case is defined by the inability or the some sort of a measure of information backflow, right? And you see that, so the dotted lines are, in this case, when we are not introducing the metric, we are defining it just by tracing out, dividing it by the trace, the old method. And the metric method is the solid line. And one more thing that I would like to tell you, the walk operator is written right there. It's a two-step walk where the thetas are changing one after the other, the parameters of the coin by which we are rotating our coins, right? But then there is a loss gain functions where L1 and L2 are these functions which are giving you equal loss and gain in the two states of your coin. And they are dependent on this parameter gamma. And as you change gamma, you are changing the degree of hermeticity, non-hermeticity. And at one point, if you go beyond the limit, the PT symmetry will break down, right? And those points are called exceptional points. We see that the metric formalism actually identifies these exceptional points very well. The jumps that you see in the solid lines exactly happens at the metric, at the exceptional point where the PT symmetry breaks down. And this phase transition in the information backflow is not seen when you are looking at this dynamics through the other definition that we showed you, right? The nonlinear definition. And the second thing that we looked into was the entanglement between the coin and the position. As I said, the algorithms on which these quantum walk algorithms are based on these properties, the ballistic properties and all those things, they depend heavily on the interaction between the coin and the position space of the quantum walk, and how the entanglement between those two changes due to the noise outside is very important to these algorithms and simulation techniques also. So we see that as you introduce the non-hermeticity with the metric mechanism, you will actually, what we see is that, so this is not a mathematical proof, but it's a numerical indication that for the asymmetric cases, the entanglement entropy does not really change in the asymptotic limit, but for the symmetric walks, which go on both sides, it actually decreases. And we have, I mean, there are many other studies using this, but this is one of the graphs that I would like to show you. So this is, this will be my talk. Thank you.
Thanks, Himanshu, for sharing your.
Yeah, the next talk is by Yogesh, and he will tell us about time and space complexity of query algorithms.
Hello, good evening everyone. I'm Yogesh and I work in complexity theory in theoretical computer science. So I'll talk on time and space complexity of query algorithms. So let me start by defining what query algorithms are. Before I do that, the central question in theoretical computer science is about understanding computational devices. And so we mathematically formulate those computational devices. and form these model of computation. And there are these various model of computations like Turing machines, quantum machines, communication protocols, and many more. The model of computation that I'll focus on today in my talk is this query model of computation. So this model is very simple model of computation and very concrete model of computation, yet it's very natural and powerful model of computation. So let me define what this model of computation is. So the setup is as follows. So we have a Boolean function on n bits. So this Boolean function might be encoding your problem. For example, let's say there is a n-node graph and you want to find out whether there is a k-click or not. You can encode that as a Boolean function. So this function is our problem, and this is known to the algorithm. What is not known to the algorithm is the input itself. And the algorithm does not know the input, but it has query access to the unknown input. So what it can do is it can learn about x by asking queries of the form, what is the value of xi, what is the value of x5, what is the value of x3. And once it has enough information, the goal will be to output the value of the function while minimizing the number of queries. So goal is to output the value of the function on this unknown input by asking queries, and the goal is to minimize the number of queries while achieving this goal. So one can formally define what a query algorithm will look like. A query algorithm that computes your function has to output the correct function value on each x, and the query complexity of a function will be the query complexity of the best algorithm that solves your f. And the query complexity of an algorithm will be defined for the worst case input. So I've defined this d dt of f is the query complexity of your function. So let me give an alternative definition for this query complexity. Your query algorithm can be seen as a binary tree, because you will form some strategy. Your strategy will look like something like this. You will query some variable, let's say x5 you are querying, and depending on the evaluation of x5, you will choose to query some other variable. For example, if x5 comes out to be 0, you query x4. If it comes out to be 1, you query x2, and so on and so forth. And once you have enough information that you are able to determine the value of the function, you will output the value of the function. So any query algorithm can be represented as a binary tree. And the number of queries on the worst case input will be the depth of this binary tree. So the query complexity that I defined in the previous slide can also be defined as follows. So it is like minimum depth of a binary tree computing f. Similarly, one can define size complexity of a function, which will be size of a minimum size of a binary tree computing your function f. So let me give you some simple examples. For example, let's say you want to compute and on n bits, which is equal to 1 if and only if all the variables are set to 1. So the following tree, you can easily verify that it computes your AND function. Whenever you see a 0, you know the answer of your function is 0. But as long as you see ones only, you have to query everything. So you can easily argue that this is optimal binary tree or optimal strategy or optimal query algorithm for the AND function. The depth of this tree is n, so your query complexity is n, and your size of this tree is n plus 1. So query can be thought of as analogously, like in informal terms, as a time complexity measure, and the size measure can be thought of as space complexity measure. Because if you will try to store this strategy or this query algorithm, you would need like n plus 1 size, because you have this n plus 1 leaves are there and n nodes are there. So around like order n number of space you would need to store this algorithm. So this is another example. Let me skip this. So now that we have defined this query algorithms, let me also define randomized query algorithms. The algorithms which don't use randomization, I'll call them deterministic query algorithm. In randomized query algorithm, there are two differences. One difference is now algorithm also have access to unbiased points, unlimited number of unbiased points, although we won't need unlimited number of random coins. The second difference is the goal is relaxed a little bit. Now you're not, you can make some error. On an unknown input x, you have to output the correct answer with probability, with good probability, let's say 2/3 probability. And this should hold no matter what the unknown input x is. Okay, so that's our goal. And again, we would like to minimize the number of queries. Again, one can formally define the query complexity measures similarly. And one can again represent these randomized query algorithm as binary trees. The only difference, only twist will be now in the binary tree, there can be nodes where you won't query anything, but you might be just doing some random coin tosses. And based on the decision of those random coin tosses, you will choose to go either left or right on your binary tree. And remember, the goal is that no matter what the unknown input is, you would want to be correct with probability 2/3. Again, randomized query complexity F will be minimum depth of a randomized decision tree which solves your functions with probability, let's say 2/3. Similarly, randomized size can be defined. And we'll ignore coin tosses in this case, only query will be counted. Since I've defined my model of computation and these randomized and deterministic decision trees, let me start by telling about problems that we have been working on and the kind of results that we have obtained. The first problem that we have worked on is proving deterministic size lower bounds for composed functions. So for a Boolean function f and g of arity n and m, let f composed with g be a Boolean function of arity mn, where you first apply g on your input, and then on the output of g you apply f. So that is composed function, f composed with g. And now one can ask, like, can we prove deterministic size lower bounds in terms of properties of f and g? Okay. And with joint work with Meena, we were able to show that that the deterministic size complexity of f composed with g is exponential in deterministic query complexity of f and the rank of g, where this rank is a combinatorial parameter. I'll give you a proof by a definition by picture. For a binary tree T, rank of a binary tree T is the largest depth of a largest complete binary tree embeddable inside your binary tree, inside your strategy, inside your query algorithm. Okay. For example, on left there is a binary tree, and one can show that you can embed a complete binary tree of depth 3, but you can't embed a binary tree of depth 4. So rank of this binary tree is 3. And then rank of a function you can define as a minimum rank of a binary tree computing your function f. So this is the rank parameter. So again, let me flash the theorem that I flashed earlier. So this size lower bound of the composed function is in terms of query complexity of f and the rank measure of your outer function g. So as a corollary, we obtain results like if f is composed with the 2-bit XOR, the size will be like 2 to the query complexity of f. Let me skip this iterated composed function, but let me mention this corollary because we'll again come to this. So this AND to OR to, so iterated composed function is when you take a function and compose it iteratively some k number of times. Okay, so this f sub superscript tensor k is a notation which says f is composed k times with itself. So this AND to OR to, when you compose it log n times, using our theorem, you can prove that the size of this function will be 2 to the omega n. And this result earlier was known due to some other techniques by work of Jukna, Razborov, Savick, and Wagner. But this result now follows from our result as well, and we have now more general result about this. So the second type of problem that we have worked on is about the role that randomness plays in these query models. Okay. For example, one can ask what advantage does randomness buy us in case of query complexity or size complexity of a function. And there is this beautiful work of Nissan from 89 which says that the deterministic query complexity and randomized query complexity can only be cubic apart. So which means that you cannot get a tremendous saving. They are polynomially related. Okay. And the size question, like you can ask the same question about size as well. This question has didn't garner enough attention before our work. And for this and or function iteratedly composed log n times, Sachs and Wigderson showed that the depth of this function will be n to the theta of n to the 0.753, which shows that size of this function will be 2 to the order n to the 0.753. And earlier I showed you from that corollary that deterministic size of this is 2 to the omega n. So this tells us that randomized size and deterministic size can be very far apart. Okay, but it seems that on the log scale things are still polynomially related. Okay, so that's where we ask the question like is randomized size and deterministic size polynomially related on the log scale? Okay. And with joint work with Arkadev, Nikhil, Jaikumar, and Swagato, we were able to show that the log of deterministic size and log of randomized size can at most be quartic apart, ignoring the polylog n factors where n is the input dimension. Okay. Now we studied the basic query model where you are allowed to query only variables. Now you can allow querying other classes of function, and this will give you more generalized query models. For example, you can say that the algorithm is able to ask parity of subset of variables. That will give you parity query model. Or you can say that algorithm is allowed to ask AND of subset of variable. That will give you AND query model. And similarly, you can define AND OR query model where you are allowed to ask AND of subset of variable or OR of subset of variables. And again, you can ask in these model of computation what is the role of randomness. So in parity model of computation, one can show that for OR and AND function, the query complexity, randomized query complexity is order 1, while the deterministic complexity is omega n, which shows that parity query model of computation, randomness can give you tremendous saving. Okay. In AND query model of computation, we asked the same question, and this question was posed an open problem in a recent survey by Noob, Lovett, McGuire, and Yuan. And we resolved this question with same set of authors, that the AND query complexity, deterministic AND query complexity and randomized AND query complexity can only be cubic apart, again ignoring the polylog n factors. And similarly for AND OR decision trees, we were able to show that randomness cannot buy you enough. It can only give you so much. For example, for AND OR decision tree, deterministic query complexity and randomized query complexity can be quartic apart. So I'll conclude, I guess. So I told you about some of the problems that we have been working on. The first problem is this deterministic size lower bound for composed functions. And we have now a method which proves the size lower bound in terms of properties of your inner function and outer function. Second is the type of problems that we looked on is this role of randomness in various query models. And we are able to show that randomness does not bias enough on the log scale in terms of size in the ordinary query model. And in the AND query model and the AND OR query model, again, the randomness only buys you so much. They are polynomially related query complexities, randomized and deterministic query complexities. Yeah, thanks. If there are any questions.
Thanks, Yogesh, for this nice talk. And then next talk is by Debabruto Deb, and he will tell us about the effect of anisotropy in highly magnetized white dwarfs.
Hi. Good evening, everyone, and thank you for this opportunity to present my work in this event. So, the work I am going to present today is titled as Studying the Effects of Anisotropy on the Highly Magnetized White Dwarfs in General Relativity. And by magnetized white dwarf, we are going to basically focus on the super Chandrasekhar white dwarfs and study the effects of combined effects of anisotropy and magnetization on the super Chandrasekhar white dwarf. And I am going to tell you later what is actually super Chandrasekhar white dwarf. So, last day actually Manjari discussed the evolution of the stars, and she has actually focused in the lower panel where the star is the main sequence star has large mass above 10 solar mass, and how it is actually actually reach to the end phase of neutron star or black hole. So, for the totality I am going to present the upper panel evolutionary phase for the stars, where the mass of the star is less than 10 solar mass. Then actually what happens when the fusion of the hydrogen just tends to end, then the star actually increases to the red giant, and when it reaches to the red giant, at that time the helium fusion happens to produce the oxygen and carbon, but the mass of the red giant is not enough to provide the temperature at the core to again fuse the carbon and oxygen to having the fuel for the star, and as a result the red giant actually removes the outer layer by forming the planetary nebula, and it leaves behind some carbon core, what is actually white dwarf. So, white dwarf is actually some star which is supporting the extreme inward gravitational pull by the degenerate electron gas pressure. So, note that I am saying here the white dwarf is made of degenerate electron gas. This is because we are considering there is no strong interaction like neutron star here, and electrons are mostly not interacting by themselves, and we are considering them as a simple gas. So, in 1935, in his seminal paper Chandrasekhar, this is actually the picture of the Chandrasekhar paper. In Chandrasekhar actually employed the equation state for the electron, where he has applied the Fermi-Dirac statistics, and immediately one have the number density for the electron, and by applying the simple technique of statistical mechanics, one can have the energy density and pressure. So, you have the equation state for the electron. Now, applying the force balance equation and the mass balance equation, you can have the, obviously this is the Newtonian regime, not the general relativistic effect has not been considered at that time. So, Chandrasekhar arrived to the mass radius relation for the white dwarf, and there is an interesting part. You can see that if you consider n equals to 3, then the mass of the white dwarf becomes independent of the central density, and it arrives into the limiting mass for the white dwarf, which is the 1.4 solar mass. So, let us now discuss what is supernova. A supernova is an extremely luminous stellar explosion that involves disruption of actually the entire star, and it is so much luminous that it is almost 10 to the power 10 times luminous compared to the sun actually. So, there are actually majorly two type of supernova are there, type 1 supernova, type 2 supernova. So, type 1 supernova event can be classified into 3 parts, type 1a supernova, 1b and 1c. So, type 1b and 1c actually reduces into the black hole, whereas the type 2 supernova reduces into the neutron star. And note that all these 3 types of supernova are actually core collapse supernova. Whereas we are more interested about the type 1a supernova, which is actually the results from the thermonuclear explosion of the carbon oxygen white dwarf when its mass actually approaches to the critical mass limit, that is the 1.44 solar mass. So why I mean even astronomers are more interested about the type 1a supernova because of their unique characteristic of light curve. So in the left hand side plot you can see the light curve for the in the plot in the left hand side you can see light curve for the different type 1a supernova, and based on the luminosity the decaying is happening. So for the higher is the luminosity, decay rate is less for the type 1a supernovae for those cases, and this is actually Phillips relation. And if you apply time scale crunch factor, you can actually merge into a unique characteristic for the type 1a supernova. That's why it is actually treated as standard candle or standardized. They can be made as a standardized candle. And this standard candle has I mean, there is a significance of it, how we are presently looking at the universe nowadays. Why so? So let me discuss that. So before that, you know, if you know luminosity of a source, absolute luminosity of a source, then you can easily derive the distance of the luminous object by applying the inverse square law. So type 1a supernova, that's why actually considered as a standard candle, because it has remarkably similarity in brightness, which can be, as I said, standardized in considering the distance between the observer. So 24 years ago, the Sol, two teams led by respectively Sol Perlmutter and Brian Schmidt, they actually declared that the expansion of the universe is accelerating, which is a Nobel Prize winning discovery, and it immediately leads to the presence of the dark energy, which is now widely accepted. And the one of the basic assumption behind this work was they have considered type 1a supernova as the standard candle. And one may again ask what is the reason behind the such enormous luminosity of the type 1a supernova. This is because of the radioactivity of the nickel 56, which again decays into cobalt and then iron, and these two reaction to decay into cobalt and iron, for these two reaction the half time is basically 7 days, 6 days and 77 days, which actually shows what is the length of the this light curve width. So these are the all reasons why actually type 1a supernova has been considered as a standard candle. But the problem arises like this. Immediately, recently it had been seen that there are some overluminous type 1a supernovae and underluminous type 1a supernovae. So I am just trying to focus on the overluminous type 1a supernovae. So you can see from this plot, the supernovae within the circle is basically highly overluminous, and they are not following the Phillips curve, what the usual type 1a supernovae should follow. And the luminosity is actually related to some mass energy and the kinetic energy of the ejecta velocity. But it has been found that for those cases ejecta velocity is very low. So entire luminosity is coming from this mass energy thing. And further it has been seen that the nickel mass found for this type 1a supernova is as high as 1.8 solar mass. But normally it can be seen for the normal type 1a supernova, the nickel mass critical limit should be like 0.85 solar mass. So you can see the nickel mass is much higher for this peculiar type 1a supernova. And if you just try to predict what should be the mass of the progenitor white dwarf, it should be as high as 2.8 solar mass. So it becomes, this is really a setback to the community. So this is known as actually super Chandrasekhar white dwarf. So immediately researcher came with two competing model, merging of massive white dwarfs and explosion of rapidly rotating white dwarfs. But both two scenario failed to explain the highly massive 2.8 progenitor white dwarf. And later Mukhopadhyay and collaborator actually came up with a solution by introducing magnetic field. They able to show that they can explain such highly massive progenitor white dwarf. So it is difficult from observation to tell what is the magnetic field inside the star, and so it requires some theoretical model to tell the strength of the magnetic field and how it affects the physical parameter of the magnetic field. So again there it can be found that the magnetic field inside the white dwarf can be as high as 10 to the power 14 Gauss, as shown by this researcher. So now it can be seen that Chu et al. Has been shown that using the orientation of the magnetic field, it can be solved whether maximum mass of the compact star is rising or decreasing. And by magnetic field orientation, they mean that when the magnetic field is along the radial direction, it is radially oriented, and when it is along the transverse direction, it is transversely oriented. Although they have introduced this idea, but they failed to explicitly discuss all these things and introduce in the force balance equation and to study what the effect of magnetic field and if there is anisotropy due to the magnetic field and its orientation on the compact star. So in our work, we have actually applied this idea of magnetic field orientation and actively, and further we have assumed an important idea, that is we have considered that anisotropy is arising due to both local anisotropy of the fluid and the presence of the magnetic field, and we are going to see that it will play a crucial role for the magnetized compact star, for the stability of the magnetized compact star. So now if you consider a isotopic system, the stellar structure equation looks like the equation 1, where the left hand side term is the hydrodynamic force, the first right hand side term is the gravitational force, and the red term is the anisotropy due to the magnetic field. So if you consider isotopic system, the anisotropy comes due to the magnetic field as you can see as the red term. So at the center, when you consider, so at the center you can see that anisotropy is proportional to the magnetic field, but at the center the gravitational force and the hydrodynamic forces are 0. But the anisotropic force is not 0, as a result it immediately disbalances the stability of the system. So to resolve this issue, we have actually considered the anisotropy is made of, anisotropy has combined effect due to anisotropy due to the matter and anisotropy due to the field. And considering this the effective anisotropy due to fluid and matter, we are able to resolve this issue. I am quickly skipping all this for the less time. So we have considered the equation state like this as shown in equation number 6, and to bound the system we have considered a functional form for the magnetic density dependent magnetic field profile, considering Bandyopadhyay et al. And based on all this, we are able to solve the TOV equation for our case, and you can easily see that we are able to show a stable stellar structure equation for white dwarf, where using anisotropy due to both the magnetic field and fluid, we are able to explain the 2.8 solar mass higher the progenitor mass, and for the transverse orientation, and for the radial orientation we can also able to explain the lower mass compared to the 0 magnetic case. So another interesting thing is like for the radial orientation, based on the chosen different parametric value, we are able to explain the different set of sub, super and standard Chandrasekhar white dwarf in a single mass radius curve. And you can see different combination there, like the sub and standard, sub and super, and the standard and super Chandrasekhar white dwarf. So through this work, so we are able to solve some important aspects, and this is the take home message like this. Using the combined effect of anisotropy due to fluid and magnetic field, we are able to show that for the magnetic field, it is essential that you need to consider combined effect of anisotropy due to fluid and magnetic field. Also, our work has shown that we should be cautious about considering type 1a supernova as considering standard candle. Obviously, it has a significant implication on the modern day idea of the cosmology and so. And obviously, another thing we are able to show that based on the choice of the free parameter, we can accommodate all the combinations sub and super Chandrasekhar and standard Chandrasekhar white dwarf in a single mass radius curve. So, all of this, thank you for your attention. And this work has been published to FJ, and I am grateful to the co-authors, Bani and Fridolin, for their significant contribution. Thanks.
Okay.
Thanks a lot, Devabrata, for this nice talk. So the next talk is by Aman, and he will tell us about QC thermodynamics for nuclear models.
Okay, so I'll be talking about nuclear models which are written at high densities and what they can tell us about the thermodynamics of quantum chromodynamics. So if you look at the phase diagram of quantum chromodynamics, in the title I have written conjecture because a lot is not known about this phase diagram. In this figure, on the x-axis we have the baryon chemical potential, or equivalently the baryon density, and on the y-axis we have temperature. Both are in the units of MeV. So most of our knowledge about this phase diagram comes from lattice QCD. So from at low baryon densities close to 0, we know that the transition from a confined hadronic phase to a deconfined coagulon plasma phase is a crossover transition, and it happens at nearly 156 MeV. As we move towards higher baryon density, we find that we expect that the transition should change from crossover to a first order phase transition. However, we do not know where this line lies. We do not know where the critical endpoint lies, at what baryon density. If we go to still further baryon densities, at low temperature and high μb, we have a little bit idea from the neutron star physics studies, but again we do not know at what baryon chemical potential or the baryon density the transition from confined to deconfined phase occurs. We also don't know what the state of the ground, the phase of the ground state is, whether it is a color superconducting state, some inhomogeneous state, or something else. So most of our knowledge is limited to low baryon densities from lattice QCD and also some collision experiments, and also a little bit to the low T, low temperature and high μb region from neutron star studies. Of course, the fundamental QCD Lagrangian is known, but even so, one cannot do the calculations so easily. So in such a scenario where it is difficult to make calculations from first principles, we use what are known as models, hadronic models. So these hadronic models are basically some Lagrangians in which the degree of freedom is are the hadrons, the baryons and the mesons. So these models are written keeping some particular region of the phase diagram in mind. For example, one such model is hadron resonance gas model, which works well at small baryon densities near the temperature axis. And on the other hand, we have some nuclear mean field models which work well at high baryon densities and low temperatures. So before I move on to the nuclear models, I will talk a little bit about the hadron resonance gas model. So in this model, one has a system of baryons and mesons, which are known from lattice QCD and some quark models. It contains both stable particles and resonances, but otherwise it does not contain any interactions. Resonances are attractive in so through the inclusion of those resonances, the model has some attractive interactions, but otherwise it is a free collection of the baryons, mesons, and resonances. This hadron resonance gas model has had some successes. For example, if one looks at the pressure of the hadron resonance gas model at 0 baryon density and compare with lattice QCD, one finds a very good agreement up to the critical temperature. Also, the hadron resonance gas model has been successful in predicting the yields of the different baryons from a thermalized system. But it also has some problems. One is that the model does not incorporate chiral symmetry and its restoration. Chiral symmetry is an important aspect, important and known aspect of QCD, but it is not included in the model. And because chiral symmetry is not included, one cannot study the effect of the critical modes. So if you look at this phase diagram, if the critical endpoint exists, then in that case, one expects certain fields to become massless as one comes closer to the critical endpoint. And it is expected to have experimental signatures. But because chiral symmetry is not included in HRG model, one cannot study the effect of these critical modes. One more thing, in this phase diagram, at low temperatures and baryon densities, we know that the system is made up of hadrons. And if the system is made up of hadrons, one should have a universal hadronic model which works well both at high densities and at low densities, because one doesn't expect the interactions to be different in different regimes. So keeping this in mind, some people have applied HRG model at high densities, but it is now known that the result it gives are in contradiction with known facts at high densities. Another important problem with the HRG model is that it does not have repulsive interactions. So if you look at this plot, this has been taken from HotQCD 2020 paper. On the y-axis, one has the second derivative of pressure with respect to baryon chemical potential. And on the x-axis, one has temperature. If one looks at the magenta line, which is the HRG result, and compare it to the green line, the gray line, which is the continuum lattice result, there is a reasonable agreement up to Tc, which is represented by the yellow band. However, if we move on to the fourth order derivative of the pressure with respect to baryon chemical potential, and now compare the magenta line with the gray line, one finds there to be significant differences, not only at Tc, but also below. So, hadron resonance gas model clearly fails in explaining these derivatives of pressure as seen from the comparison. So the question is, what is the resolution? This is a plot from paper by Guru Prasad et al. In this, again, the authors have plotted the lattice QCD data given by the points and error bars. The purple line is the HRG result without any interactions, and the green dashed line is HRG result by including the repulsive interactions. So as seen from the plot clearly, the inclusion of the repulsive interactions improves the agreement with lattice greatly. So this comparison of HRG and lattice tells us that the repulsive interactions are important in any hadronic models, but are not present in the original HRG. Now we come to nuclear models. So these models, these Lagrangians are written keeping in mind the physics of high density, and the degrees of freedom are much fewer compared to the HRG type models. So the degrees of freedom in this case are represented by psi, which represents proton, neutron, and possibly some strange baryons. Then there are the interaction terms mediated by sigma and the omega meson. Sigma meson is responsible for the attractive interactions, while the omega meson is responsible for repulsive interactions. And as we just saw, the repulsive interactions are important in explaining the properties of thermodynamics of QCD. So the idea behind the present study is to solve these models at high density and extrapolate those results at somewhat intermediate densities, and then compare it with the lattice results and see how good the agreement is. If the agreement is good, then it shows us that the models, the hadronic models have somewhat universal character. They can explain both high and low density physics. While solving these models, one must also keep in mind some constraints. For example, in heavy ion collisions, NQ by NB equal to 0.4 is related to the charge to baryon density ratio in the colliding nucleus. And the other constraints such as mu q equal to 0 and mu s equal to 0 are just convenience, because the calculations are somewhat easier in this case. So now we come to some results. So here in this plot, we have the value of the mean fields, basically how much the omega and the sigma are contributing as a function of the baryon density. So the red ones represent the omega field, and the green one represents the attractive sigma field. The sigma field is proportional to the scalar density, which is always non-zero, and hence even at mu b equal to 0, it has a non-zero value. The omega interaction, the repulsive interaction, is proportional to baryon density, and therefore it goes to 0 as mu b goes to 0. And as seen from the plot, it is clear that both the attractive and the repulsive interactions are important at finite mu b. So this is one of our results. In this plot, on the y-axis, we have the fourth order, the ratio of fourth order to second order derivative as a function of mu b. The green band is a result from lattice QCD for this result. The plum colored line is the hadron resonance gas model result without any interactions, and the orange line is a result from the nuclear model. As one can see clearly from the plot, there is a significant difference between the non-interacting HRG result and the nuclear model result with finite interactions. And the nuclear model result also matches with the band from lattice QCD. In this plot, we have a third order derivative with respect to baryon chemical potential, but also a first order derivative with respect to the strange chemical potential. Because of this strange chemical potential derivative, the majority of contribution to this plot comes from only the strange baryons. The light green colored band is again the lattice result, and plum colored line is the non-interacting HRG result. The orange result is from the nuclear model. In this case, we find that the orange result doesn't match with the light green color band. This is most likely due to the fact that the lattice result, of course, contains the entire hadronic spectrum, including all the strange hadrons. Whereas the nuclear model we have contains only 2 strange hadrons. It is my expectation that if one includes more hadrons, there can be an agreement between the nuclear model and the lattice for this case also. This plot is also important because it is sensitive to the strange baryons, and thus also the strange omega coupling, which is not the case in other plots. So if one can obtain a good agreement between the nuclear model and the lattice, one can also possibly constrain the omega coupling with the strange baryons. Now I come to my final result. On the y-axis, we have temperature scaled by the critical temperature, and on the x-axis, we again have the baryon chemical potential. The green band is the crossover line known from lattice QCD, and the pink band is a result from the nuclear model. Each point in the pink band corresponds to energy density, which is given in the title. This energy density is the energy density corresponding to the crossover transition at 0 mu b. It is known from lattice QCD that at small baryon densities, the crossover line and the chemical freeze-out line coincide. In our study, we have assumed that this thing happens at a constant energy density, which is given in the title. In the study, we have assumed that this thing holds at finite mu b as well, that the crossover line, the chemical freeze-out line is also a constant energy density line at high densities. So assuming that the pink band should represent a chemical freeze-out line at high densities. So if this is the line of chemical freeze-out, any phase transition should happen only at a higher, above the band. From the lattice QCD, it is also known that T by T naught for the critical endpoint lies below a value of 0.85. If it lies in a range of 0.8 to 0.85, then we get the gray band. And from the intersection of these two bands, one can put a lower bound on the location of the critical endpoint. So now I will summarize. From our study, we have found that for many of the results, the high density data extrapolated to low baryon densities does match the lattice bands. As one can see in the plots, the lattice bands have quite a width, and if one has a more precise data in future, then that can, so one can make a more precise statement from such a study. Model is of course limited due to the lack of degrees of freedom and also the lack of knowledge about the couplings. At low densities, the repulsive interactions rapidly go to 0. So the mean field first order result, since it is 0, it is important that at low densities we have a beyond mean field calculation. And by combining hadron resonance gas and inputs from nuclear model, one can perhaps build a more universal hadronic model which works both at high and low densities. And the way these models are written, they can in principle be modified to include chiral symmetry, and one can then directly study the critical endpoint within the model. Thank you.
Thanks, Aman, for your talk. And we have the last talk of our session. So our final, but so they are being loaded. So the final talk of the session is by Orko Prabhu Ghoshal, and he will tell us about his recent studies. His talk is being loaded, so he's changed the title a little bit, so that's why. Yeah, he will tell us about local unidentifiability of quantum states and its application. Thank you.
Okay, thank you. Good evening, everyone. So first of all, I'm very much thankful for giving me this opportunity to present my talk today. So today I will going to talk about local unidentifiability of quantum states and its application. Now, this term seems to be very weird because local unidentifiability of quantum states is very unfamiliar to us. So what does it mean is that this is a type of state property that can only arise in multipartite quantum systems. So what do I mean by multipartite quantum system is that, so there are spatially separated labs, and each of the labs holding quantum particles. And these labs can locally manipulate these quantum particles, as well as they can use classical communication for their communication purpose. Now these multipartite quantum states share some sort of correlation that cannot be created via local manipulation as well as classical communication. Now one may ask, yes, in quantum mechanics many things happen, many things may not happen. So let's consider that these multipartite quantum states hold this particular state property, that it is locally unidentifiable. But what is the real life application of such thing? Does it have any real life application? Because we are interested in a real life application. So today I will not go in any technical details. I will try to motivate what is the real life application of such thing. So whether this correlation exists in nature or not was first proposed by us, and this is available in this archived version, and these are the authors. Okay, so let us start with the very basic concept of a banking system. So we all know, we are all aware about a banking system. Okay, so there is a bank, and two participants created a joint account in the bank. So one account holder is Alice and another account holder is Bob, and they share a common bank account, right? Okay, so we know the banking system that if I want to make a transaction, then bank will provide me a OTP. Okay, so after getting that OTP, I can transact, I can debit my money. But since there is a constraint here, because since this is a joint account, so Alice cannot actually debit or transact any money without the consent of Bob, and vice versa, right? So both of them actually expect that bank will provide them a security, right? So complicated scenario happen when, for example, Alice want to debit some money, but Bob has no consent. Okay. So in this case, in classical physics, many things can happen. Alice can apply many strategies. Okay. Alice can hack Bob's computer, and Alice can manipulate him using phone calls. So many things can happen, but this will question on the security of our banking system. So let us consider that there is a bank, and the bank provided each of the holder the information about the space, that the OTP will come from a sample space having 4 particular alphabets A, B, C, and D. And let us consider the one-time password is ACD. Okay. Now the member of the bank, what he wants? He wants that individually any account holder cannot gain the entire information of the one-time password, because if he gain the entire information, he can actually make a transaction without the consent of the another. So he will actually distribute or share this one-time password in such a way that the individual member cannot decode the one-time password. They has to come to a common place and decode it, and then they will decide whether they make a transaction or not, right? But this Alice and Bob, they want to cheat the bank, and they want to cheat one another, right? The only freedom I have given them, that they can use phone calls and they can locally manipulate their degrees of freedom. Okay. So in this case, what Alice and Bob wants? So Alice and Bob wants to certainly predict the one-time password using their freedom. Okay. If they fail, then they will apply a second strategy. They will at least guess what is the letters in the OTP. If they guess exactly, if they guess the letters with 100% probability, then obviously there will be a chance of guessing the proper OTP much higher than the worst case scenario. Here by worst case scenario, I mean if they guess randomly. Okay. So then there will be a question on the security of the banking system. Okay. But the bank member is very clever. So they use the help of quantum mechanics. So they use some kind of encoding strategy. So the member cleverly encodes each of the letter from the sample space in Bell states. Now these Bell states are basically 2 spin-half particle states, and these 2 spin-half particles share some fundamental quantum correlation that cannot be realized by local operation and classical communication. So these states can be practically, these states exist in nature, and we can create these states in lab. Okay. So somehow they encode each individual letter in Bell state. Say for example, A is encoded in phi plus, B is encoded in phi minus, C is psi plus, and so on. Now each of these Bell states can be written as a linear superposition of Pauli Z basis. Now there is a surprising nature of these 4 orthogonal Bell states. What is the nature? The nature is the following, that if I provide one of the Bell state from this set and I distribute this set to 2 spatially separated observer or spatially separated lab, and I ask them a question that what state I have given to you, can you answer me correctly? The answer is no. They cannot certainly answer what will be the state. So this particular thing reveals a type of non-locality that cannot be realized using local operation, that means locally operating in my lab, and classical communication. So this type of non-locality doesn't appear in classical physics, in classical states or classical correlation. So the banker actually, they actually do the encoding in such states to secure the password actually. But there has to be a tighter condition. So this is a first criteria of the security. Okay. So let us consider this particular example. So the bank provided each of the account holder the information about the sample space. The sample space contains 3 specific letters A, B, and C, and the OTP will be of 2 letters. Say for example AC. So the OTP contains specific letters from that sample space in a specific order, right? And Alice and Bob know about the encoding. Okay. They know what will be the sample space, what will be the encoding. What they do not know is that which 2 Bell states has given to me and in which order. Okay. So the bank kept that thing in secret. Now if I ask Alice and Bob individually that you have the freedom of doing a local operation and classical communication. Now can you guess the OTP certainly? The answer is no. Why? Because if I choose any 2 random Bell states from a set of 3 Bell states, the possibility is 3p2, that means 6. In 6 possible ways, I can actually make a set of 6 elements. So the dimension of the Hilbert space will extend. So there will be a set of 6 possible elements, and these 6 elements itself becomes locally indistinguishable. So if I provide one element from this set between Alice and Bob, then they cannot certainly predict what is the element. So this gives rise to another form of non-locality that is much more general than local indistinguishability. That is known as locally unmarkability. So unmarkability means that two things are possible in unmarkable set, in unmarkable set of states. That means if I choose my encoding from a set of unmarkable set, then either Alice and Bob cannot reveal the letters as well as the order, or other thing happen. They may reveal the letters, but they may not reveal the order. Okay. So this seems to be a secure protocol, but it is not, because if I ask Alice and Bob that can you guess the letters from this OTP, can you at least guess the letters? You cannot guess the order. Okay. Can you guess the letters? The answer is surprisingly yes. They can guess the letters with 100% probability. So the banking system fails. That means why? Because the worst case probability here is increased. So initially we thought that the worst case probability is 1 by 6. But since they can certainly predict the letters, they can predict it is A and C, but they do not know the order. So in this case, there will be 50-50% chance of success and failure. So this gives rise to a question that does there exist much more stronger non-local states in nature via which I can actually do some encoding and I distribute my encoded state between 2 account holders, and they cannot reveal the order as well as they cannot reveal the identity of the OTP. So in this case, if I increase my sample space from 3 to 4, that means A, B, C, D, and I choose 2 words for my OTP, then surprisingly the answer is no for each of the question. That means in this case the Alice and Bob cannot reveal the letters contained in that OTP and the order. So this is much more secure protocol. And if the bank member apply this particular encoding strategy, then this will be a much more secure protocol than the previous one. And furthermore, we can actually generalize from a 2-party to a 3-party, and beyond 3-party, 4-party, and so on. So for example, if there are 3 account holders and we play the same game, then actually the protocol will be much secure if we encode our alphabets in a specific GHG basis. Okay. So in this case also, every member has to collaborate and come to a common lab and then decode the message. Okay. Otherwise, they cannot decrypt or decode what is the OTP actually. So there is no problem of eavesdropping and as well as authentication problem that I have discussed earlier. So in this case, the worst case probability is much low. It is 1 by 1680. It is much low. And as we increase the number of parties, the worst case probability will gradually decreases. So this ensures that this particular if we use this particular correlation, that is locally unidentifiable quantum states, and if we use in an encoding strategy, then in real life application we can get quantum advantage that classical things cannot give us. Okay. So in summary, what I want to say that the story which I have told you is actually known as a secret sharing. This is one actually application of a secret sharing. So here OTP is actually a secret, and I fix a group of people and I distribute this secret among them, and I do not trust the individual person, but if they actually collaborate in a particular lab, they can decode the message. Okay. So this is actually equivalent problem. Now as I have mentioned earlier, that locally unidentifiable quantum states has a complicated state space structure, and some kind of stronger non-locality is associated with this particular type of states. That is much stronger than local unmarkability as well as local indistinguishability, and we can utilize these particular states to actually discriminate to any kind of strings. For example, one application can be entanglement distillation. So in entanglement distillation, we often need to actually identify a string of quantum states. So we are thinking about it, but we do not know that whether we can utilize this particular state space structure in other real life application. But this is one of the thing I have mentioned. So I want to first of all I want to thank Professor Guru Prasad Kaur, Professor Shibashish Ghosh, Professor Somshubra Bandopadhyay and Dr. Manik Munik for their fruitful discussions. Thank you.
Thanks, Arko, for this very interesting talk. And we end the session here. We thank all the speakers for the very nice talk, the audience for staying put up. And also special thanks to all our students and postdoc. We only gave 15 minutes time to them, but all of them did a very fascinating job, very professional talks. And I thank you everyone for doing this. Thank you. And no. So, this concludes this session, but we have the concluding session, for which I hand over to our director.
I know everybody is quite tired, but however, I cannot, leave this place without, thanking everybody that, who are involved in this very beautiful celebration. So it's indeed, it's great pleasure, also honor for me to be part of this celebration from the day one actually, which started last year. I think it is 2nd of January. This was just after, COVID was actually, slowly disappearing from our minds. Okay, it was still there. In fact, I could not come for this celebration because in, my home there was somebody who was not keeping very well. So I had to stay at home, but the program happened here. Okay, not in this auditorium, but in the library building, simply because we had this fear of, not, safe in a closed place actually. So it was organized in the library building, and we had many people who were, asked to sit far away from each other, and many alumni, also faculty, students, everybody participated. So that is how we actually started this celebration actually. And it continued with quite a lot of talks, because it's an academic institution. So we can celebrate only in one way. The way is actually to do science, communicate science. So we had lots of talks, and there were complaints also, there were too many talks that we cannot attend. So it went, we actually overdid, okay? But it is for good only, okay? It is not a waste of time or money or anything, because it is very important for an academic institutions to have academic programs. We compensated, in fact, all that we could not do for 1.5 years during COVID actually. So in fact, actually, if you count the number of talks, it is there, all of them are there in the web, in our YouTube and web pages. And I thank, 2 people who were involved. One was Arijit in the name of HACOM. He organized several interesting talks, heritage talks, special lectures and things like that. The other one is Sayantan. These 2 people, with the help of their teams, they organized. So these two of my colleagues actually made this auditorium all the time busy. Okay, it will cry actually, and the next year probably it will take a big rest. Okay, so it was filled, and then we had high tea almost every second day. Okay, so all of us actually put on weight. Okay, including me. In fact, 1 year before I was actually 5 kilos less. And now actually I gained 5 kilos actually, and I guess it is because of the IT that was out. So I thank the administration for actually providing, wonderful, snacks, okay, that nobody will forget actually. People who complained about talks, probably enjoyed the IT. Okay, so it was something that our administration managed to provide to all of us. Okay, so that's how this, the celebration was going on for last 1 year. We had several speakers coming and, demonstrating things, including, this hydrogel stuff that our DAE, do research on it actually, and also showed, how it can be used in our institute. And many people from other organizations came and talked about their work. The importance of science and, and scientists, including about a talk on Baba, who was actually the founder of this entire organization, Department of Atomic Energy. So that's how it went on. And for the last 4 days, actually, what we had was actually, to conclude this 1 year of celebrations, we had a four days of intense talks. Okay, intense means it's really intense. As you can see, there are about 66 scientific talks, which is quite a lot, in my opinion. In fact, we could manage to get really eminent people from different parts of India, and some of them are policymakers, scientists who actually become policymakers, who shared their, views about how science should be taken to public and things like that. I must say that actually that apart from these talks by the experienced scientists, we also talks by our young colleagues, young students. Okay, that was really, really nice actually. Every day we had several talks by students and postdocs, and that was very special about our 4-day events actually. That was quite fulfilling. I think it is important that in fact those who spoke, I listened many of them actually. The talks were like talks that you hear from experienced people actually. So it is a kind of an nice thing about this program, that it also shows how well they are prepared and things like that. And also the posters kept outside were also like I used to think what is this poster is all about actually. But this time, I mean, when I listened to the students, I could see the enthusiasm in them explaining every bit of it. In fact, I was too tired on one day. About 1.5 hours I was listening to them. I said, I will listen the next one, later on actually, because it was too, they're so enthusiastic. Okay, I could see that actually I want to thank those, students who prepared these, posters outside. Some of the nice things that I felt in this meeting. Other one is actually this panel discussion, nice idea. We were happy to participate. And then a stamp release, okay, by Postmaster General. It was the idea by our chairman, Dr. Vyas, and our registrar, Srimati Vinelata, who actually took it very seriously and then talked to the most important people in postal department and got it done in a very, very short time. Without our effort, seeing this, I think it was also, the release was, was actually, it also came in newspaper actually today, I think. I've not seen it, but I saw the link actually. Okay, that was very special event to remember this. Okay, and also we had a cultural event, organized by Professor Raghavan. Thanks to him actually for this nice program. That was, there are many people I will thank separately, the team behind this banquet. And then other highlight is actually TNSF releasing, children's book, Jantar Mantar. That was a work of our IMSc staff actually, starting from Jam, Indu, Madhavan, and many people who were editors at some point. Indu is actually a current editor, and it was our idea, I think, to collect all the articles written by all of us, actually not me actually, of course all of you, also IMSc's members. And that is something that we all should be proud of, that we contributed to, society actually this way, spreading science. And I thank Indu especially for, working very hard to get it done in very short time actually. She must have worked very hard to really dig out all the articles from what, Jantar Mantar books spanning for last 20 years, more than that actually. So it is not an easy job. It is not that you Google it and get it actually. It is, you really have to actually scan through all the magazines and get the contributions from IMSc students, postdocs and faculty. That one. So I thank for that actually. And also we released Srinivas Rao's translation of one of his books actually. That was also one of the highlights. So these were highlights that everybody was happy about. So I want to thank separately to various people who are behind to make this event extremely successful. One is this overall administrative support. Srimati Vinelata, everybody knows actually by now actually that she was behind for every of the event that took place here with our the team, starting from our administrative Officer, Srimati Indra, and TSO K.P. Shankaran, and 3 JOs, Accounts Officer Srinivas Raghavan, Junior Administrative Officer Parthiban, Junior Administrative Officer Mr. Babu. So with the team, the overall administrative support was actually done. So thanks to them, accommodation and local travel were taken care of by Mr. Babu, Mr. Bhaskaran, and IMSc travels, Mr. Murthy, Mr. Rajshekharan, Mr. Sasikumar, and Paman travels for excellent service, and let's give a round of applause to these people. And travel booking, mostly air travel bookings, were done by our K.P. Shankaran. He's here actually with his team, Gokul Bharati and Krishna Kumar, and travel agent Pamela. So I want to thank all of them actually for this. And travel reimbursement is of course very important, so that the people who have come, they get what they spent actually. So our accounts officer was busy all these times actually to prepare everything. Mr. Srinivas Raghavan, Mr. Bhatmanaban, and his team actually, and media team. Of course, media team is the team who actually been working even before the meeting started. Preparing a movie for that we actually showed on the first day. I want to thank Ms. Gayatri, who has worked tirelessly to ensure recording, live streaming of talks. Also thanks to Pushpa Visuals for renting equipment and photography support. And of course, computer support. Computer support was by Mr. Ravindra Reddy. In fact, we had a short meeting with him. Actually, he said nothing bad should happen actually during this period. In fact, I sincerely thank him actually for making sure that nothing bad happened actually. Everything went so smoothly, and Mr. Srinivasan was all the time here actually. Vasan. So if I say Srinivasan, I not recognize. So Vasan was here all the time. So for everybody, Vasan is actually a buzz. It's like they're in our head actually. If something happens, it is Vasan. So that is how we are all tuned to in IMSc. Everybody who are watching IMSc for few days would realize actually, Vasan is somebody who you cannot live without actually. So he is there for everything. Okay, so let me thank Vasan. I take this opportunity to thank him actually in this event. Excellent job he had done actually. Mr. Dinesh and Mr. Nagamaleshwara, who actually, Haripriya, who are all with that team actually to make sure that electrical team, of course, Mr. Mohan is very quiet all the time. But of course, he is the one actually who actually makes every place, bright. Without him, I think, we will not get proper air conditioning, this and that, everything actually. So his team, Mr. Morgan, Mr. Tenarse, Mr. Mohan, Mr. Vijay Kumar, even though they are very quiet, but they are all very, electrified people actually. All the time busy, making sure that, we all have comfortable stay inside the auditorium with a good air conditioning and things like that. Okay. And civil team, of course. Civil team, you must have noticed actually, there were a lot of work that were done actually to make sure that when our visitors comes, they are all comfortable at this institute. Mr. Sundar, Balachandar, actually they did wonderful job, as you can see actually, because a lot of work is going on in this institute. They made sure that things are cleaned up so that our visitors actually feel very comfortable, going around the campus. Because as you can see, renovation work is going on, and they are all very busy with that actually. So I want to personally thank for making sure that everything is in order actually. And also I want to thank housekeeping, security staff, particularly Amal Raj, who actually were with them actually to make sure that the entire institute was neat and clean as usual. We are always neat and clean, and because there are more people, so we had an extra effort actually to keep it in order actually. Our gratitude to the team of post of special cover and my stamp, that we had, that I already thanked actually. And also for catering, okay, this is the most important part, as you all know actually. Without that, we would not have even entered into this room. So I want to really thank actually, this catering team for the humongous job, particularly Indu, Sushmita, Asan, Saket, and extremely hardworking staff like, Krishna Balaji, Munuswamy, Rajkumar, Ravichandran. Okay. Behind them, there were 3 people actually I want to mention. Registrar, Srimati Vinilata, KP Shankaran and Indra. They were all with them actually to make sure that we get very good food actually, all throughout the okay, so of course there was also cake. Okay. You will not forget such a big cake actually that was actually cut on that day. I want to thank I think Sushmita Gupta and Saket and also Shankaran. They apparently this was really difficult to make actually. So I came to know from Dr. Sushmita Gupta that she had to call the the bakery people actually whole day to make sure that it comes on time actually. Special thanks to her for making this to happen on that day so that we could actually do that cake cutting. Okay, so that was something very nice thing. Okay, and for arranging memento, Mr. Johnson, you can, all of us got some nice presents. Johnson worked very hard to get it done in time actually. You can see there is nothing missing in every bag actually. He got the best ones possible, so that thanks to him. And of course, the beautiful logo that you see everywhere, reminding us about this IMSc 60. I want to give a special thanks to Indumati, who made this happen. And our library staff, time to time helping me to provide, our achievements, okay, in every such events. And I want to thank Dr. Pandian and his team for providing the data on IMSc. And then website and poster, special thanks to Rahul, Gokul Balaji and Disha. And panel discussion, again Rahul, Mr. Sundar and civil staff. And decorations by Manas, Satish, Tanmay and Sushant, they are all our students actually. Which I want to specifically mention. Our students actually, they participate in every aspect of this meeting actually. Okay, there are many names, and this is an opportunity for me also to really actually see them, talk to them, because somehow it's a big institution now with 126 students. It is impossible to remember, for any human being that many, unless you are actually teaching them that particular group. So this was an occasion that I could meet a lot of enthusiastic students in this institute. Okay, so thanks to all of them who actually, came and did many things like, drawing this beautifully and putting this, eco-friendly decorations and all that. I'm thankful to them actually for taking part in all these activities. Cultural events, as I said, Professor Raghavan and Sundara Vaidyanathan who actually performed and their team actually. I want to thank them for actually making that social media, of course, Rahul Siddharthan and Varini took care of it. And I heard, even though I'm not in any social media, but I came to know from my friends that IMSc is actually there everywhere now. In the sense, actually, there were a lot of followers, following, what is happening in IMSc and tweeting and things like that. It is very nice to know that IMSc is getting more and more popular, even in social media, actually. So, and I cannot leave without thanking the following members actually. Even though I've thanked, I missed out some of them actually. Our staff particularly, you must have seen them, bringing the presents and things like that. But they did not do only that actually. They were working behind the names that I mentioned actually already in their office, making sure that everything is done before the visitors leave and the program ends actually. They are the names I want to read out. Mrs. Prema, Mrs. Ushanandini, Mrs. Geeta, Mrs. Jayanti, Mrs. Archana, Mr. Parthiban, Mr. Amar, Mr. Gopi, Ms. Sadhana, Ms. Maurya. So these are names actually, you cannot forget because they are the big team actually working in an institute and making sure that everybody was comfortable during the entire meeting actually. Student volunteers, as I said, students played an important role in this meeting. Chandrani, Vishwajit, Sushant, Anup, Sashikant, Ajaya, Ashutosh, Priyatosh, Hitesh, Nikhil, Madhumita, Rohit, Shanmugapriya, and many others actually. So if I had missed some names, apologies. And it's possible that I missed some names who contributed to this meeting, apologies. Finally, okay, I must tell, how this all started, because if I had said this, it would not have looked nice. See, if I recall actually, while we were all busy, organizing talks, listening, because, because of these two gentlemen, we, till last month, we did not really, take up this, kind of program to organize actually. So this organization started at very late stage actually. Okay, it's not that we started 6 months before. We started very late. Okay, so I realized just about 1.5 months back that it's going to be going to be January 2nd, and we didn't have any plan actually. So at that point I just called the youngest of the lot actually. Okay, there are some senior members also in the group. I called Professor Shauli, Professor Anup Dikshit, Professor Arjit Samal, Professor Arnapal, Professor Ramya, Professor Ragul Siddharthan, Professor Sakat Saurabh, Professor Sayantan Sharma, Professor Arnapal, everybody actually. These are the names. Okay, let me finish actually. So I called them to my room actually. It was about 1.5 months before. You can imagine. I think 1.5 months before. I called them. I said, we need to organize a program, small program, for a few days actually. So they jumped into this actually, the same day. I said, I won't interfere with you. That is the only thing that I said. I will not give any ideas. I will not do anything actually. Whatever you need from me, I will do it actually. So that is the promise I made actually. Because if I had done anything, this meeting would not have been successful. That I can guarantee. Because I'm not great in organizing anything. Let me accept my inability to organize things. So they actually took it seriously, and because of my less intervention, and thanks to the team led by our registrar, Srimati Vinay, we could make this program success. They actually planned everything. Everything happened, secretly in many places. They didn't even update me. Okay, I was unhappy actually, I must say. But now I forget everything, because I'm not serious actually. Don't think that I was very unhappy or anything. But the thing is actually, I did not know. If my wife asked what is the program, I said, no, I don't know. They are there. Then she used to ask, you don't know what is happening actually. You are not a director, she used to say. I said, yeah, of course. So it was like that actually. Because that was done intentionally, because if I had interfered, it would not have been successful. Okay, that I was very sure. Okay, so it was, the entire, this everything was actually sort of planned by them. Probably they had many interesting discussions, fightings, and all that actually, because it can happen in such big meetings actually. So, but end of the day, the product was wonderful. Okay, So that is what I think, in fact, you must have seen them actually. Some of them did not attend even a single talk actually. So many of them actually, I would say, they were all, and one of them is actually Shauli, despite that, she had some health issues, she was there till, the previous day of the program actually. She was with me, the final, plans when we were doing actually. Shauli was with us actually. I want to give a special thanks to her for so much energy. Being a more senior person, she really advised, in many ways actually throughout this. So special thanks to her actually. And of course, I cannot actually say, who did what actually, but all of them actually did 100% of their, effort. So I think, I owe quite a lot to these people actually. Without their, enthusiasm, interest, and you can see some of them are the, youngest lot. They actually have no idea about IMSc. Some of them, like Anup and Arnab joined about a year back actually. So I must thank them for their enthusiasm about IMSc. This is 60 years of IMSc, but they are the youngest babies of this institute who really actually did lot of things. Arjit is a youngest. Okay, the way they put in the effort, I don't think I had done in my life. Sorry. Ramya is another. Sorry, I forgot. Sorry, Ramya is the youngest. Okay, they're all very young actually, of course, compared to me. So all these guys, they did wonderful job actually. So I am, I take this opportunity to thank all of them, and above all that, actually, the people who came and gave talks from different places. Some of them are here, some of them already left. So I sincerely thank all of them who consider our institute seriously and come and gave talks. Finally, I want to thank the agency or organization which supports such nice events, Department of Atomic Energy, and our chairman Vyas. Actually, when I told him, he was very, very enthusiastic about having such a program in IMSc. Also suggested these things. So I thank the supporting agency, which generously supported to have nice programs. So thank you all for listening to me for this, some 15 minutes or 20 minutes patiently. Let's have 70 years by some of you in 10 years now actually. Thank you.